Watch the dashcam footage and you will see it before you hear anything. A quiet road outside Chelyabinsk, Russia. Gray sky, dirty snow, a line of cars crawling to work on a Friday morning. Then the top of the frame goes white. Not lightning white, something older and more violent, a light with weight to it, throwing hard shadows across the dashboard of every car for 100 miles. For about 5 seconds, a second sun is burning over Russia. It was the 15th of February, 2013, a little after 9 in the morning. 20 degrees below freezing. People were scraping windshields, dropping kids at school, standing in the ugly light of office corridors. Completely ordinary. Nobody in that city knew that the most powerful thing to touch the earth in over a century was already inside the atmosphere, and that it had left home long before there were people, or oceans, or a moon worth mentioning. The rock was small. That is the part people struggle with. About 20 meters across, roughly the width of a house, maybe 12,000 tons of stone and iron. It had spent 4.5 billion years drifting in the asteroid belt, minding its own business, until some ancient nudge sent it falling inward toward the sun, and it approached from exactly the wrong direction. It came at us out of the glare of the sun itself, which meant no telescope on Earth could possibly have seen it. It hit the top of the atmosphere at around 19 kilometers per second. Think about that speed for a moment. Roughly 68,000 kilometers an hour, fast enough to cross a country between heartbeats. At that velocity, air stops behaving like air. It cannot get out of the way in time, so it piles up in front of the rock and compresses into a plug of plasma hotter than the surface of the sun. The stone did not so much fly as detonate its way through the sky. About 30 kilometers up, it came apart. The whole mass converted itself into light and pressure in a single pulse, an airburst carrying something close to half a megaton of energy, roughly 30 times the bomb that flattened Hiroshima. For an instant, it was brighter than the sun in the sky, bright enough that people looking at it got sunburn on their faces indoors in a Russian winter. Some felt a wave of heat on their skin and could not understand where it came from. And then nothing. This is the detail that stays with me. The light came first silent, and for 2 or 3 long minutes the city just stood at its windows, staring up, filming on phones, wondering what they had seen. They did not know that light outruns sound. They did not know that the blast was still coming, crossing the sky toward them at the speed of an explosion, and that the safest possible place to be standing was anywhere except a window. When the shockwave arrived, it arrived all at once. Windows did not crack, they left their frames. Glass came into thousands of rooms as a spray of blades, exactly where people had gathered to look. A wall of a zinc factory folded and dropped. Doors blew open, alarms screamed across the whole region. In the space of a few seconds, around 1,500 people were hurt, almost all of them cut by the glass they had just walked toward. In one school, a teacher named Yulia Karbasheva did the one thing that saved her class. She had no idea what the flash was, but she told her students to get under their desks and cover their necks, an old drill for a disaster she could not name. Seconds later, the windows burst inward over their heads. The children were untouched. She had stayed on her feet by the glass to make sure they obeyed, and a flying pain cut through the tendons of her arm. Nobody died, and that is almost entirely luck. The thing burst high, and it burst over a spread-out industrial city rather than a dense old town center. Drop that same rock a few kilometers lower, or over a place built of brick and narrow streets, and we would be telling a very different story with a body count in it. As it was, Russia gave us the most thoroughly filmed cosmic event in human history, courtesy of a country where nearly everyone drives with a camera on the dash. The footage is genuinely strange to watch. People swearing softly in a dozen cars. A jogger stopping mid-stride. A traffic camera catching the flash reflected in a frozen puddle. In the hours after, the theories came fast and frightened. A missile, a plane breaking apart, a weapon. A few people, entirely reasonably given what they had just seen, wondered whether this was how the world ended on an ordinary Friday, with no warning at all. The rock itself was not finished. A large fragment survived all the way down and punched a neat round hole, about 8 meters wide, through the thick ice of a frozen lake called Chabarkal. Divers went down through that hole for months. In October, they finally hauled up the main piece from the mud at the bottom, a lump of dark pitted stone weighing over 600 kilograms. So heavy it broke the scale, they tried to weigh it on before splitting into pieces. For scientists, it was a grim kind of gift. Never before had an impact of that size been captured from so many angles. Its light measured, its sound recorded, its fragments gathered still warm from the ice. Chelyabinsk became the best-studied airburst in history, and the lesson it taught was not a comforting one. The models had underestimated how much damage an object that small could do, which meant the quiet rocks in the invisible middle range were more dangerous than anyone had assumed. Here is the coincidence that still unsettles the astronomers I have read. On that exact same day, a completely unrelated asteroid the size of an office block, one they had tracked for a year, made a close pass by the Earth. Every professional I was pointed at that known object, and while they watched the rock they could see, the rock they could not see slipped in from the dayside and went off over a city of 1 million people. So let us be honest about what happened. We did not track it. We did not deflect it. We did not even get to be afraid of it in advance. We found out it existed at the same moment everybody else did, by the light of it burning. The uncomfortable truth underneath the whole spectacle is a simple one. The sky is not being watched as closely as you would like to believe, and the sun makes a very good place to hide. We have cataloged most of the true monsters, the ones a kilometer and up, the civilization enders. Those we would likely see coming with years to spare. It is the middle range that keeps people awake. The city killers 40, 50, 100 meters across, big enough to erase a metropolis, small enough to stay invisible until the last night. We have found only a fraction of those. The rest are still out there, on orbits we have never measured, keeping their own schedule. This has happened within the living memory of the planet before. In 1908, over a remote stretch of Siberian forest called Tunguska, something came down and exploded in the air with many times the force of the blast over Chelyabinsk. It flattened around 80 million trees across an area larger than a major city. There was no crater because it never touched the ground. There was simply a region where the forest had been pushed flat, every trunk pointing outward from a single empty center, like spokes. Nobody died at Tunguska either, and again the reason is just geography. Almost nobody lived there. Run the clock a few hours differently, and that same object arrives over a European capital instead of empty taiga, and the 20th century opens with a dead city and no explanation anyone alive would have believed. The Earth has been quietly playing this game of near misses for a very long time. We have only recently started keeping score. What Chelyabinsk really did was end an excuse. Before that morning, it was easy to file asteroid impacts in the same drawer as movie plots and dinosaur documentaries. Something safely finished, something that belonged to the deep past. Then a small stone nobody saw coming injured 1,500 people before breakfast and put its picture on every screen on Earth. It was a reminder, written in broken glass, that we live at the bottom of a shooting gallery. That is the thing this whole story keeps circling back to. The universe does not send a warning. It does not build tension or give you a bad feeling in your chest the night before. The dinosaurs did not get one. Chelyabinsk did not get one. The event simply arrives fully formed, out of a clear sky, and the first sign that anything is wrong is the thing itself, already here, already happening. Keep that in mind. We're going to need it. And a 20-meter rock is nothing. It is a pebble, a rounding error, the smallest kind of thing the sky can throw at us. To really understand what our address in space can do, you have to go much bigger and much further back. You have to go to the single worst day this planet has ever had, a day that ended 3/4 of everything alive and left its signature in a thin, dark line of clay you can still put your finger on today. Picture a warm, shallow coast, 66 million years ago, somewhere that will one day be called Mexico. Ferns, the drone of insects the size of your hand. A herd of horned animals moving through the shallows to drink. An utterly ordinary afternoon in the last age of the dinosaurs. Then one of them lifts its head because there is a new light in the sky. Small at first, a bright point where no bright point belongs. And it is getting bigger. What they were looking at was a mountain falling. An asteroid somewhere around 10 kilometers wide. Roughly the cruising altitude of a passenger jet stood on end, moving at some 20 kilometers a second. It had crossed the solar system for who knows how long to arrive at this exact patch of sea on this exact afternoon. From the moment it became visible to the moment of impact was not measured in years or hours. It was measured in seconds. It struck the shallow water off the Yucatan, and it did not slow down. It went through the sea as though the sea were not there, through the seabed, and kilometers down into the crust of the planet before it delivered everything it had. The energy released was somewhere in the region of 100 million megatons. Billions of Hiroshimas, all in one place in one instant. Solid rock for many kilometers around simply stopped being solid. The ground behaved like water, dropped into water. A crater opened nearly 200 kilometers across, so deep that the floor of it rebounded upward into a ring of mountains taller than the Alps, which then slumped back down while the rock was still molten. We know the shape of that scar with real precision, because it is still down there, buried beneath the limestone of the peninsula, a perfect ghost of the worst second in the history of life. Anything within several hundred kilometers was gone in the first moments, vaporized or thrown into the sky. A pressure wave and a wall of superheated air raced outward, stripping the land to bare rock. Out at sea, the water, shoved aside by the impact, rose into waves that may have reached hundreds of meters, tearing across the ancient Gulf and running deep inland over coastlines that had never known anything like it. But the truly clever cruelty of this event was still on its way up. The impact flung a colossal spray of molten rock clean out of the atmosphere, some of it into space. And everything that goes up has to come back. Across the entire planet, this ejected material rained back down as trillions of glowing droplets, each one a spark reheating the air as it fell. For a few hours, the whole sky of the Earth glowed red-hot. An oven switched on above the surface of the world, and forests thousands of kilometers from Mexico burst into flame at the same moment. Whatever survived the fire then had to survive the dark. The impact had blasted billions of tons of soot, dust, and sulfur high into the atmosphere, where it spread into a shroud that wrapped the entire globe. The sun went out, not dimmed, functionally switched off for months and possibly years. Temperatures fell off a cliff. The warm green world of the dinosaurs became a cold black one, lit only by the fires slowly burning themselves out. In the dark, the plants stopped. Photosynthesis is the floor that everything else stands on, and when the light failed, that floor fell out. First the plants, then the animals that ate the plants, then the animals that ate those animals. The great long-necked giants, the horned herds, the tyrannosaurs at the top of it all, every one of them now trapped in a food chain, starving from the bottom up. Size, which had always been their advantage, became a death sentence. When it was over, around 3/4 of all species on Earth were gone. Every dinosaur that was not already on its way to becoming a bird. The great sea reptiles, the ammonites, those coiled shells that had ruled the oceans for hundreds of millions of years, vanished from the fossil record as if someone had drawn a line through it. Above that line, a whole living world. Below it, a different and much emptier one. Some things made it through, and it is worth asking why. The survivors were mostly small and mostly clever about hiding. Things that could burrow underground and wait. Things that lived in water and fed on the dead matter drifting down. Small feathered creatures and small furred ones, our own distant grandparents, no bigger than a rat, riding out the apocalypse in a hole in the ground. Every human who has ever lived is descended from something that survived that winter by being unimportant. For most of human history, we had no idea any of this had happened. The dinosaurs were simply gone, and the theories for why were a bit of an embarrassment. Disease, badbacks, stupidity, mammals eating all their eggs. It took a father and son, a physicist and a geologist, both named Alvarez, to notice that the answer had been sitting in the rock the whole time, in a thin band of gray clay you could hold between two fingers. Walter Alvarez, the geologist, was trying to work out how long that clay layer had taken to form. His father, Luis, the physicist, suggested measuring a rare metal called iridium, which drifts down from space at a slow, steady rate. If the layer had formed slowly, it should hold only a trace. Instead, they found a spike dozens of times more than there should be. Then colleagues found the same spike in Denmark, in New Zealand, everywhere they looked. The whole planet wore the same strange line. Iridium is scarce in the rocks of the Earth's surface, but it is common in asteroids. A worldwide layer of it, laid down in a geological instant, pointed to only one thing. Something enormous and rich in metal had struck the planet and thrown itself into the air as dust that settled over the entire globe. In 1980, the Alvarez team said it plainly. The dinosaurs were killed by an impact from space. A lot of very respectable people thought they had lost their minds. There was one glaring hole in the argument. If a rock big enough to do this had hit the Earth, then where was the crater? For over a decade, the murder had a weapon and a fingerprint, but no scene of the crime. The answer, it turned out, had already been found years earlier by a man looking for something completely different, and then quietly filed away in a drawer where nobody thought to look. His name was Glenn Penfield, a geophysicist mapping the Yucatan for a Mexican oil company in the late 1970s. In the magnetic data, he saw an enormous buried ring, a symmetry that nature does not usually make, nearly 200 kilometers wide and centered on a village called Chicxulub. He suspected what it was, but the data belonged to the oil company. Key rock samples had been lost in a warehouse fire, and the world was not ready to listen. So it waited. It all came together in the early 1990s. Researchers connected Penfield's buried ring to the Alvarez layer, tracked down old drill cores, and finally found the proof. Shocked quartz, its crystal structure hammered by pressures only an impact can produce. Glassy droplets of rock that had been melted and flung and frozen in flight. The crater matched the age of the clay layer exactly, as near as the rock could tell. The weapon, the fingerprint, and the body were at last in the same room. And there is a small, cold detail I love about all this. The village that gave the crater its name, Chicxulub, sits almost dead center over the point of impact, entirely by chance. The name comes from the old Maya language. Depending on who you ask, it means the tail of the devil or the horns of the devil. A people who could not possibly have known what lay buried beneath their feet had named the place after a demon. In recent years, a site in North Dakota called Tanis may have handed us the impact hour by hour. In its rock, a paleontologist named Robert De Palma found fish that appear to have died within an hour of the strike, thousands of kilometers away, choking on tiny glass beads of impact debris lodged in their gills. Sturgeon and paddlefish, flung up a river valley by the shaking of the whole continent, buried alive. It may be the most detailed snapshot of a single terrible morning in the entire fossil record. So, this is not a hypothetical. It is a thing that has happened, that left a receipt 200 kilometers wide and a line of clay around the entire planet. The dinosaurs ruled for 160 million years, far longer than we have managed anything at all, and it took the sky roughly 10 seconds to end them. They had no space program. They had no telescopes. In fairness, neither did we, until embarrassingly recently. The rock that did it came from the asteroid belt, that crowded ring of rubble between Mars and Jupiter, and those bodies at least keep to orbits we can eventually map and predict. Given time, given money, given attention, we could see the next one coming. But the belt is not the only place death is stored. Far beyond the last planet, out where the sun is just another star, there's a second reservoir, vast and dark, and almost impossible to watch. And every so often, something falls out of it. Go outside on the right night, and you might catch a comet, hanging there with its tail combed back, quiet and beautiful and apparently harmless. Enjoy it. Then remember where it came from and how fast it is moving. Because a comet is a mountain of ice falling toward the sun at a speed that would cross the gap between the Earth and the Moon in a couple of hours. And the ones we never see coming fall from a place we can barely believe is real. Wrap your head around the shape of the solar system for a second. The planets, the asteroid belt, everything you picture when you picture space, all of it is crammed into a thin disk close to the sun. Around that disk, like a shell around a yolk, there is thought to be an enormous sphere of frozen bodies called the Oort cloud. It begins far beyond the last planet and reaches perhaps a quarter of the way to the nearest star. Nobody has ever seen it directly. The numbers are almost meaningless, so let me try anyway. The outer edge of the Oort cloud may sit a full light year or more from the sun, tens of thousands of times further out than the Earth. Drifting in that immense cold dark are perhaps 1 trillion icy bodies, maybe more, each one a comet in waiting. They move so slowly, so far from the sun's warmth, that a single loop around it can take millions of years. Most of them will never come near us. We only ever worry about the ones that fall. The cloud is named for a Dutch astronomer, Jan Oort, who worked out in 1950 that the long-tailed comets we see could not simply be coming from nowhere. Something had to be feeding them in from a reservoir far outside the planets, in every direction of the sky. He never saw it. He inferred it, the way you infer a hidden room from the draft under a door. 70 years later, it is still a place we know only by its visitors, an entire structure of the solar system that remains, technically, a theory. Here is what makes these visitors so different from the asteroid that killed the dinosaurs. The belt is a flat ring, and its rocks keep tidy, repeating orbits we can chart. The Oort cloud is a sphere, so its comets can drop in from any angle at all, from above, from below, from behind the sun. They spend almost all of their vast orbit invisible in the deep dark, and only light up once they're already falling through the inner solar system. By the time we notice them, they are close. They also hit harder. An asteroid from the belt catches up to us at a fairly civilized pace. A long-period comet has fallen from the very edge of the sun's grip, gathering speed the whole way, and can arrive at the Earth's orbit at 50, 60, even 70 kilometers a second. That is several times faster than the Chelyabinsk rock. And the energy of an impact climbs with the square of the speed. So a comet the same size as an asteroid can strike with many times the force. Worst of all is the warning. A dangerous asteroid, if we're watching, might give us years or even decades to plan. A new long-period comet gives us months, sometimes only weeks, from the night it is first spotted to the day it crosses our path. There is no catalog of them, because they have never been here before in recorded history, and most will not return for longer than our species has existed. Each one is a stranger, arriving unannounced. In January 1996, a Japanese amateur named Yuji Hayakitake was sweeping the sky before dawn with a pair of powerful binoculars from Hilltop. He found a faint smudge that should not have been there, a comet nobody had ever recorded. Within weeks, it brightened into one of the great comets of the century, passing close to the Earth and unrolling a tail that stretched halfway across the sky. It was glorious. It was also discovered barely 2 months before its closest approach. Sit with that timing. A mountain of ice came out of the outer dark, swung past our planet closer than most comets ever do, and we met it as a surprise found by one man with binoculars. It missed us by a comfortable margin, so it became a beautiful memory rather than a catastrophe. But the discovery window was the whole point. If its aim had been a little different, 2 months is not a great deal of time to do anything at all. For a long time, all of this stayed theory and near miss. We knew comets could hit planets in the way a loaded gun can go off without ever having watched it happen. Then, in the summer of 1994, the universe arranged a demonstration, live, on the largest planet in the solar system, with every telescope on and off the Earth pointed at it. For the first time in history, humans knew a collision was coming and knew exactly when. The year before, 3 seasoned comet hunters, Carolyn and Eugene Shoemaker and David Levy, had found something bizarre near Jupiter. It was a comet, but it had been smeared out into a line, a string of bright beads, each trailing its own little tail like a squashed pearl necklace. Jupiter's immense gravity had already caught this comet on an earlier pass and torn it into more than 20 separate fragments. Now those fragments were swinging back around, and this time they were going to hit. So astronomers did something that had never been possible before. They marked the calendar. From the 16th to the 22nd of July, 1994, one fragment after another would slam into Jupiter, and we would get to watch it happen. There was real uncertainty over whether we would see much at all, since the impacts would land just around the far edge of the planet, out of direct view, rolling into sight only minutes later as Jupiter turned on its axis. They saw plenty. The fragments came in at around 60 kilometers a second and detonated in Jupiter's clouds with a violence that stunned even the people who had expected it. Fragment G, one of the larger pieces, hit with an estimated energy of some 6 million megatons. That is hundreds of times the entire nuclear arsenal of the Earth at its peak delivered in a single blow. It left a dark bruise in Jupiter's atmosphere larger than our whole planet, a scar you could pick out through a backyard telescope. For a week, Jupiter wore a row of black marks strung across its southern clouds, each one a place where a piece of a single comet had gone off like a world-ending bomb. Those scars lingered for months, and the lesson landed hard. This was not the deep past, not a story read out of the rock. This was a collision happening now, in our own solar system, at a scale that would have sterilized the Earth many times over, watched live on television. There's a comfort people like to reach for here, the idea that Jupiter is our great protector, a giant vacuum cleaner sweeping up comets before they can ever reach us. There's some truth in it. Jupiter's gravity really does capture and fling away a great many objects, but cuts both ways. That same gravity also flings objects inward toward us and can bend a harmless comet onto a collision course with the Earth. Our supposed guardian is not always on our side. Long before we understood any of this, comets terrified people for the right reasons and the wrong ones. A new light in the sky with a tail like a drawn sword was read as an omen of plague, of the death of kings, of the end of the world. We laugh at that a little now, but strip away the superstition and the old fear was pointing at something genuinely real. A comet is a true harbinger. It simply does not care who the king is. Somewhere in the Oort cloud tonight, a comet that has never been named is beginning to fall. It may have been nudged loose a million years ago and is only now drifting into the region where the sun's light will finally wake it. We will not see it until it is well inside the planets, glowing, with a tail beginning to grow behind it. If it happens to be coming for us, we will have that same cruel handful of months and a front row seat to our own approach. And comets are slippery in a way rocks are not. As the sun heats a comet, its ice turns straight to gas and jets off the surface, and those jets act like tiny, uneven rocket engines. They can shift a comet's path in ways that are genuinely hard to predict, right up to the very end. So even once we have spotted one, pinning down exactly where it will go is harder than you would hope. The thing is, in effect, steering itself badly in the dark. What unsettles me about comets is not their power. The dinosaurs already proved the sky can hit hard. It is that they are patient and hidden, stored by the trillion in a shell we cannot see, waiting for a nudge that may have come a million years ago. But a comet is at least a visitor, a thing from far away. To find the next threat, you do not need to look out into the dark at all. You only have to look up in daylight at the star we have always trusted most. We call it constant. We build our lives, our crops, our entire idea of a normal day around the quiet assumption that the sun will simply keep doing what it does. It rises, it warms, it sets. But the sun is not a calm lamp bolted to the sky. It is a churning ball of nuclear fire more than 1,000,000 times the volume of the Earth, and every so often it loses its temper and hurls a piece of itself directly at us. It has done exactly that within living memory, and we came within a week of finding out what it would cost a world like ours. On the 1st of September, 1859, an English astronomer named Richard Carrington was sketching sunspots in his private observatory, as he did most clear mornings. He had the sun's disk projected in front of him, safely dimmed. Suddenly, two brilliant beads of white light flared up among the spots. So bright, they briefly outshone the rest of the sun's surface, then faded within a few minutes. Carrington was almost certainly the first human being to watch a solar flare erupt. He had no idea he had just seen the opening move of a global event. What Carrington witnessed was an explosion on the sun carrying the energy of billions of nuclear bombs, throwing out radiation and, more importantly, launching an enormous cloud of magnetized gas into space. We call that cloud a coronal mass ejection. Billions of tons of the sun's own outer atmosphere, flung off at millions of kilometers an hour. And this particular cloud, by pure bad luck, was aimed almost straight at the Earth. Normally, such a cloud takes 2 or 3 days to cross the gulf between the sun and the Earth. This one moved so fast, along a path already swept clear by an earlier eruption, that it made the crossing in about 17 hours. So while Victorian astronomers were still writing up the curious flare they had seen that morning, the thing it had launched was already most of the way here. And the night sky was about to do something that frightened people half to death. The auroras came first, and they came everywhere. Curtains of red and green light, normally a polar spectacle, spilled all the way down toward the equator. They were seen over Cuba, over Hawaii, over Colombia, places that never see them. In the Rocky Mountains, gold miners got up and began cooking breakfast at 1 in the morning, convinced by the glow that dawn had arrived. In the northeastern United States, people could read a newspaper outdoors by the light of the sky alone. Then the technology started to misbehave, and this is the part that should worry us. The telegraph was the great advanced network of 1859, wires strung across whole continents. The geomagnetic storm pushed electric currents into those wires, currents nobody had put there. Operators took shocks off their equipment. Telegraph paper caught fire. And strangest of all, some operators found they could disconnect their batteries entirely and keep sending messages, running purely on the electricity the sky was forcing through the lines. In 1859, that was a curiosity, an anecdote for the newspapers. The world ran on horses, gaslight, and steam. A telegraph line going haywire was an inconvenience, nothing more. The Carrington event arrived at almost the last possible moment in history when a storm of that size could hit the Earth and do essentially no lasting harm. And we have spent every year since then making ourselves more vulnerable to the exact same thing. Because think about what we have built since. A civilization wired end to end and utterly dependent on it. The power grid, the satellites your phone talks to, the navigation signals that guide ships and aircraft and stamp the time on every financial transaction on Earth. The pumps that move water and fuel and sewage. All of it, in the end, is electricity flowing through conductors. And a large enough geomagnetic storm reaches down and pushes its own unwanted currents into every one of those conductors at once. The soft spot at the heart of it all is a piece of equipment most people have never once thought about. The large power transformer. These are the giants of the grid, some the size of a house, that step voltage up and down so electricity can travel long distances. A big geomagnetic storm can drive currents into them that they were never designed to handle, overheating their cores until the copper inside begins to melt. And here's the ugly part. They are not sitting on a shelf somewhere waiting to be swapped in. The biggest transformers are custom built, often to order, in a small handful of factories around the world. One can take a year or more to manufacture and deliver, and each weighs hundreds of tons. Lose a few, and you can route power around them. lose hundreds in a single afternoon, all across a continent. And there is no warehouse to raid, no quick fix, no way to build replacements fast enough. Whole regions could sit without power for months. Some sober estimates say longer than that. Try to picture a modern city without electricity for months, not hours. No water pressure once the towers drain, because the pumps are dead. No refrigeration, so the food spoils. No heating and no cooling, no fuel, since the pumps at the stations run on power too. No functioning hospitals once the backup generators burn through their diesel. The lights going out is the least of it. Everything we quietly rely on to keep millions of people alive in one place runs at the bottom on the grid. We have already had a taste of it. In March 1989, a storm far smaller than Carrington's swept across North America. In about 90 seconds, it overwhelmed the power grid serving Quebec, and 6 million people lost electricity in the depths of a brutal Canadian winter. It came back within a day, but that was a minor storm, and it still dropped an entire province in a minute and a half. The Carrington event was many times stronger than the one that did that. There have been others since. Storms around Halloween in 2003 knocked out satellites, forced airliners off their polar routes, and caused a blackout in Sweden. Astronauts on the space station have had to shelter in the most heavily shielded part of their craft, while radiation from a flare washed over them. Every one of these was survivable. Every one was also nowhere near the size of the event Carrington watched erupt through his telescope. The truly big one has not visited the modern world yet. It has, however, come extremely close. On the 23rd of July, 2012, the sun let loose a monster. A coronal mass ejection at least as powerful as the Carrington event, and by some measure stronger, tore off the sun and blasted across the inner solar system. It ripped straight through the Earth's orbit at tremendous speed. There is only one reason it did not hit us and throw the 21st century into chaos: timing. The Earth had rolled past that exact spot in its orbit roughly a week earlier. We know all of this because a sun-watching spacecraft called Stereo, it happened to be sitting right in the line of fire and took the full blast, measuring it in fine detail. Scientists went through the data and were, frankly, rattled. One respected space weather physicist put it about as plainly as it can be put. If that cloud had left the sun a week earlier, we would still be picking up the pieces. We did not dodge it because we were clever. We dodged it because we happened to be somewhere else. So how often does the sun throw something that big? Honestly, we are not sure, and that uncertainty is a worry all its own. Estimates for the chance of a Carrington-scale storm actually striking the Earth run to a few percent, or in some studies well over 10% in any given decade. Play that out across a human lifetime or across the working life of a power grid, and it stops sounding rare. It starts sounding like something we should probably have a plan for. There's a sliver of good news here, and it deserves to be said. Unlike the comet and the asteroid, a solar storm does give us a little warning. The flash of light and radiation arrives in about 8 minutes, but the dangerous cloud of gas behind it takes a day or more to reach us. That single day is everything. It is just barely enough time, if we are watching and if we act, to power down the most vulnerable parts of the grid on purpose and let the storm pass over deadlines. The catch is that riding out the storm means deliberately switching off the power in order to protect the machines that make the power. It means choosing a controlled blackout over an uncontrolled catastrophe. That is a brutal call to make on a day when the sky looks perfectly ordinary and every instinct and every politician is telling you not to plunge millions of people into darkness on the say-so of a distant satellite. We would have to trust the warning completely. History is not encouraging on that score. There is something almost personal about this particular threat. The asteroid and the comet are strangers, cold visitors from far away. The sun is family. It is the reason there is any life here at all. The engine that grows the food and warms the oceans and hangs the same sky over every human who has ever lived. To realize that the very same star could reach out on an ordinary afternoon and quietly unplug our whole civilization is a strange and sobering feeling. The hand that feeds us is not always a gentle one. And a solar storm, for all its menace, is a tantrum, not a destiny. The sun would flare, we would suffer, and given time we would rebuild, wiser and better shielded. It is survivable, but the sun has a slower plan for us as well. One that no shielding, no warning, and no clever engineering could do a single thing about. Because the same steady star that keeps us alive is also very gradually running out of the fuel that lets it. Every second, deep in its core, the sun fuses roughly 600 million tons of hydrogen into helium, and it has been doing that for 4.5 billion years. That cannot last forever. Nothing that burns can. And when a star like ours begins to change, it does not fade away quietly. It swells, and it brightens, and it turns at last on the very worlds it once kept alive. Long before the sun dies, it will kill the Earth. And that clock is already running. Move forward in time, far enough that the word future stops meaning very much. Stand on the Earth if there is still ground to stand on, and look up. The sun fills a third of the sky, a vast sullen dome of dim red light. The oceans are long gone. The rock underfoot is bare and cracked and hot to the touch. This is not some disaster that struck the Earth from outside. This is the Earth's own star, growing old, and doing to this planet exactly what stars eventually do. We treat the sun as the very definition of permanence. When we want to promise that something will last, we say it will be here as long as the sun still rises. But the sun is a thing that is burning, and everything that burns is on a schedule, whether or not it bothers to tell you. Ours is a middle-aged star, a little under 5 billion years old, and roughly halfway through the calm, stable stretch of its life. The trouble is what stable actually means over that kind of time. For now, the sun sits in the long, comfortable phase astronomers call the main sequence, patiently fusing hydrogen into helium in its core and holding itself in near-perfect balance. Gravity pulls inward, the heat of fusion pushes outward, and the two have fought to a draw for billions of years. It is the steadiness of that standoff that has given life the vast stretches of time it needed to crawl out of the sea and eventually build telescopes. But the balance is very slowly shifting. There's a quiet catch that most people never hear about. The sun is getting brighter. As it fuses hydrogen, its core slowly fills with helium ash and contracts, which makes it burn hotter and pour out more light. The change is glacial, roughly 1% brighter every 100 million years. You would never notice it across 100 lifetimes. But stack up enough of those tiny percentages, and you get a slow-motion catastrophe with a deadline written into it. The first thing to go will not be dramatic. No fire, no explosion. Just heat, rising and rising, until it crosses a line the Earth cannot come back from. In somewhere between 1 and 2 billion years, the sun will grow bright enough to tip our planet into what is called a runaway greenhouse. The oceans start to evaporate in earnest, and here lies the trap. Water vapor is itself a powerful greenhouse gas, so more heat makes more vapor, and more vapor traps still more heat. Once that cycle takes hold, there's no stopping it. The oceans boil away into a thick, scalding atmosphere of steam. The water rises into the upper air, where sunlight breaks it apart, and the hydrogen leaks off into space, so the planet does not merely heat up, it dries out permanently. Every ocean, every lake, every river that has ever existed on Earth, lifted into the sky and then lost for good. What remains behind is a hot, dead rock under a crushing haze. If that sounds familiar, it should. We keep a preview of it next door. Venus, almost exactly the same size as the Earth, very likely had water once, and then tumbled into precisely this kind of runaway heat. Today, its surface is hot enough to melt lead, wrapped in clouds of acid, crushed under a pressure that would flatten a submarine. That is the Earth's own future, written on the planet next to ours. The sun will simply turn our world into a second Venus, given enough time. And complex life may bow out well before any of that. As the sun brightens, the slow chemistry of rock weathering pulls carbon dioxide out of the air faster, and plants need carbon dioxide the way we need oxygen. Long before the oceans boil, perhaps in as little as a few 100 million years, the level could fall too low for most plants to survive. Remove the plants, and you remove nearly everything that eats them, or that breathes the oxygen they make. The living world may fall quite early. So let us be clear about the timescale, because it cuts both ways. A few 100 million years is a terrifyingly firm eviction notice. It is also an almost unimaginable stretch of time, far longer than complex life has yet existed. If anything descended from us is still around to watch the oceans begin to steam, it will be as different from us as we are from the first fish. Whether that thought is comforting or bleak, I honestly cannot decide. But that is only the warm-up. The real transformation comes much later, around 5 billion years from now, when the sun finally exhausts the hydrogen in its core. With the fire at the center guttering, gravity wins for the first time in the star's life, and the core begins to collapse and heat. That heat ignites a shell of hydrogen around the dead center, and the outer layers of the sun respond by doing something spectacular and terrible. They begin to swell. This is the red giant phase, and it is the settled fate of our star. The sun bloats outward, its surface cooling to a deep angry red, even as its total output soars. It does not grow by a little. It grows to dozens, then hundreds of times its present size, a monstrous dim balloon of thin gas. From any world close enough to survive, it would no longer be a disk in the sky. It would be the sky, a wall of red filling the view from one horizon to the other. As it expands, it devours its own children. Mercury, the closest planet, is swallowed first, dropping into the swelling star and vaporizing without ceremony. Venus follows, that hot, dead twin of the Earth, gone the same way. The inner solar system, the warm, rocky heart of everything, is simply consumed by the star that made it. And then the growing edge of the sun reaches out toward the orbit of the Earth. Whether it actually swallows the Earth is one of those beautifully grim, open questions. As the sun swells, it also sheds mass, loosening its gravitational grip, so the Earth's orbit should drift outward, away from the danger. But a swollen sun also drags on a nearby planet like a hand moving through water, pulling it inward. The current best guess is that the two effects fail to save us, and the Earth spirals in and is devoured. Even in the Kinder version, our planet is left a charred cinder, circling a star that has cooked it clean of everything. Picture the last day of the Earth as a living world. The sun a seething red vault overhead. The rock of the surface heated past melting, running in slow, bright rivers. Every mountain we ever climbed, every city we ever built, every fossil of every creature that ever lived, all of it softened, then liquid, then gone. 4.5 billion years of history, from the first cell to the last human thought, wiped off the face of the planet as though a hand had been drawn across a fogged window. The sun does not stop there, though its own end is now close. After the red giant phase, it burns heavier fuel in unstable pulses, growing and shrinking, shrugging its outer layers off into space in great expanding shells. For a while, those glowing shells make something genuinely lovely, a planetary nebula, a luminous ghost of gas lit from within. Our sun will paint one of these across the dark, a tombstone the width of the solar system, for anyone left to see it. And at the center of that fading beauty sits whatever is left of the sun. No explosion, no black hole. Our star is not heavy enough for either. Just the exposed core, crushed down to roughly the size of the Earth, yet still holding half the mass of the sun, so dense that a spoonful would weigh as much as a truck. We call it a white dwarf. It no longer burns anything at all. It simply sits there, glowing white hot from leftover heat, with nothing left to do but cool. And cool it will, for an almost eternal span of time. A white dwarf fades so slowly that the universe is not yet old enough for a single one of them to have gone fully dark. Over trillions of years, our sun's ember will slide down through orange, red, and finally into a cold, dead, invisible lump of crystallized carbon adrift in the black. A diamond the size of a planet, unlit, unwarmed, unremembered. That is the true final state of the star we owe our entire existence to. There's one thread of hope woven through all of this, and it is worth holding on to. None of it is soon. We have hundreds of millions of years before the Earth turns hostile, billions before the sun turns on it directly. That is enough time, in principle, for our descendants to become something that no longer depends on this one fragile planet, to spread out, to leave. The death of the sun is a certainty. Our death inside it is not, at least not yet, not if we are clever and very, very patient. But a colder truth sits underneath that hope. Even if we escape our own star, we will not have escaped the problem. Every star dies, and most do not fade away gently over billions of years the way the sun will. Some stars, the big ones, the bright, furious ones, die all at once, in an instant of violence bright enough to be seen clean across the universe. And one of them is hanging in your sky right now, on the shoulder of a familiar constellation, already running low on time. You have almost certainly seen it already. Find Orion, the hunter, on a winter night, and look to the bright star marking his upper shoulder. It carries a faint reddish tint if you study it. That star is called Betelgeuse, and it is dying. Not in billions of years. Perhaps tonight, perhaps 100,000 years from now, but by cosmic reckoning, it is standing right at the edge of its grave. And when it falls in, we will have the best and most frightening seat in the house. It is a clear winter night, and the constellation Orion is climbing the eastern sky. 3 stars in a row for his belt, and above them, marking his shoulder, a single bright star with a faint ember glow. Most people walk past it their whole lives without a second thought. But that star, Betelgeuse, is one of the most closely watched objects in the sky, because astronomers know something about it that changes how you see it. It is going to explode. The only question is when. Betelgeuse is a red supergiant, and the word supergiant is not decoration. Drop it where the sun sits, and its surface would swallow Mercury, Venus, the Earth, Mars, and reach on out toward the asteroid belt. It is something like 700 times the width of the sun. It is also young, only around 10 million years old, an infant beside our middle-aged star. And that youth is exactly the problem, because Betelgeuse has been living catastrophically fast. This is the brutal bargain that massive stars make. The more mass a star has, the harder gravity squeezes its core, the hotter it burns, and the faster it tears through its fuel. A star like the sun sips its hydrogen over 10 billion years. A giant like Betelgeuse, perhaps 15 or 20 times heavier, burns through everything in only a few million. It shines tens of thousands of times brighter than the sun, and it pays for that brilliance by dying almost as soon as it is born. To understand how it dies, you have to look inside it. As the star runs low on hydrogen, it starts fusing helium into carbon, and when the helium runs out, it fuses carbon into heavier things still: oxygen, neon, magnesium, silicon. Each stage is faster and more desperate than the one before. The star becomes like an onion, shell inside shell inside shell, each burning a different element, all of it racing inward toward a swelling core of iron. And iron is where the whole thing ends. Iron is the ash that kills the fire. Every fusion reaction up to iron releases energy, and that energy is what has held the star up against its own gravity for its entire life. But fusing iron takes energy in rather than giving it out. So the instant the core turns to iron, the furnace does not merely slow down. It stops. The one thing propping up a star heavier than 20 suns simply switches off, and it switches off in less than a day. What happens next is almost too fast to describe. With nothing left to hold it up, the iron core, about the mass of the sun packed into a ball the size of a city, collapses in on itself in roughly a quarter of a second. The infalling matter is crushed so hard that protons and electrons are jammed together into neutrons, and the core suddenly stiffens into something as dense as the nucleus of an atom. The collapse slams to a halt, and everything still plunging inward hits that wall and rebounds. The rebound, along with an almost unimaginable flood of ghostly particles called neutrinos, blows the entire outer body of the star apart. This is a supernova. For a few weeks, a single dying star can outshine its whole galaxy, all 100 billion of its sibling stars combined, releasing more energy in that short flash than the sun will radiate across its entire 10 billion year life. And at the center, where the core used to be, it leaves behind something small and strange and impossibly dense. In late 2019, Betelgeuse gave the world a scare. It began to dim, noticeably, dropping to a fraction of its usual brightness over the course of a few months. Astronomers and headline writers alike started wondering out loud whether we were watching the final flicker before the blast. It turned out to be a false alarm. The star had coughed out a huge cloud of dust that cooled and briefly veiled it. But for a while there, a great many very serious people were watching Orion very, very carefully. When Betelgeuse does finally go, and it could be tonight or 100,000 years from now, it will be a spectacle like nothing in recorded history. For weeks it would blaze in our sky bright enough to see in broad daylight, bright enough to throw faint shadows at night, a second point of hard white light where a dim red star used to hang. Then, slowly, over months, would fade, leaving Orion permanently missing a shoulder and a tiny, dense corpse spinning where the star had been. And now, the reassuring part, followed immediately by the unsettling one. Betelgeuse is around 600 light-years away, which is comfortably too far to hurt us. We would get the light show and nothing worse. But that raises the obvious question. How close would a supernova have to be before the light show turned into a killing? Where exactly is the line drawn? The rough answer is somewhere around 50 light-years. Set off a supernova closer than that, and the problem is no longer the light. It is the radiation, a wave of high-energy gamma rays, and later a slow rain of cosmic ray particles, would wash over the Earth and go straight to work on the thin layer of ozone that shields the surface from the sun's ultraviolet light. Strip that ozone away, and the everyday sunlight that feels so harmless becomes something that sterilizes. It will not be a fireball or a shockwave that got us. It will be quieter and crueler than that. The base of the ocean food chain, the tiny plankton living near the sunlit surface, would be scorched by ultraviolet light. Crops would fail. The chemistry of the atmosphere would sour, possibly darkening the sky and cooling the climate for years on end. A supernova does not have to touch you in order to kill you. It only has to be close enough and aimed nowhere in particular, which is to say aimed everywhere. We have watched these deaths for a very long time without understanding them. In the year 1054, Chinese astronomers recorded a guest star that appeared suddenly in the constellation we call Taurus, so bright it stayed visible in daylight for over 3 weeks. They had no way of knowing they were watching a star die around 6,000 light-years away. Today we can aim a telescope at that exact spot and see the shredded, still expanding wreckage, a beautiful tangle of glowing gas we call the Crab Nebula. There were others in the historical record. A blazing new star in 1006, the brightest ever set down, bright enough to read by at midnight. One in 1572 studied by Tycho Brahe, and one in 1604 studied by Johannes Kepler. And then silence. Since the invention of the telescope, not one star in our own galaxy has been seen to explode. Statistically, we are due for a supernova, perhaps overdue. There may be a star out there whose light is already on its way, carrying news of a death that happened while the pyramids were still being built. The closest we have come in modern times was in 1987, when a star exploded in the Large Magellanic Cloud, a small galaxy orbiting our own, safely outside the danger zone. For the first time, our instruments were ready and waiting. And in a strange preview of the physics, detectors buried deep underground picked up a burst of neutrinos from the dying core, a full 3 hours before the light of the explosion reached us. The ghost particles outran the fire. We felt the star die before we ever saw it. Now, for the turn in this story, the part one find genuinely beautiful. That same violence, that same catastrophic death, is the reason you exist. The calcium in your bones, the iron in your blood, the oxygen filling your chest right now, all of it was forged in the hearts of massive stars, and, in the heaviest cases, in the very explosions that ended them, then scattered across space to seed new worlds. A quiet star like the sun could never have made you. So every supernova is a paradox hanging in the sky. The most destructive single event a star can produce is also the great act of creation in the whole universe. The only process violent enough to build and scatter the raw material of planets and oceans and living things. We are quite literally the cooled ash of dead stars, briefly arranged into something that can look up and be afraid of the next one. There is a dark poetry in that I have never quite gotten over. As for the next one, we keep a list. Betelgeuse is the famous name, but it has company. Antares, the red heart of the scorpion, is another supergiant near the end. There are more scattered across the sky, and at least one closer candidate, a dense stellar corpse called Ike Pegasi, only around 150 light years away, that could one day die in a different and equally violent way. None are quite close enough to be certain killers. The emphasis there belongs firmly on the word quite. That is what changes about the night sky once you know all this. It stops looking like a peaceful field of fixed, eternal lights. It starts looking like what it truly is, a room full of enormous furnaces at every stage of burning down, some steady, some flickering, a few already dead, and simply waiting for the news to reach us. Most are harmless. A handful are loaded, and you cannot always tell from down here which is which. But a supernova, for all its horror, has one saving grace. It throws its death outward in every direction at once, so its fury is spread thin across the whole sky, and by the time it reaches anything far away, it has weakened. Distance protects you, unless, that is, the dying star finds a way to gather all that violence, aim it, and fire it in a single narrow beam. Because a rare kind of star could do exactly that. And if one ever points at us, distance will not save us in the slightest. In the late 1960s, at the coldest depth of the Cold War, the United States lifted a series of satellites into orbit called Vela. Their job was to watch for the telltale gamma-ray flash of a secret Soviet nuclear test in space or on the ground. The satellites worked. They caught flashes of gamma rays again and again. There was just one problem. The flashes were not coming from the Soviet Union or from the Earth at all. They were coming from deep space. For years, the discovery sat classified, a genuine mystery locked inside a military secret. When it was finally handed to scientists in the 1970s, nobody had the faintest idea what could produce such a thing. Brief, random flares of the most energetic light in existence, popping off from every direction of the sky, roughly once a day from somewhere far out in the dark. It took decades to work out the answer, and the answer turned out to be worse than anyone had guessed. These flashes have a name now, gamma-ray bursts, and they are, without any competition, the most powerful explosions in the universe since the Big Bang itself. When one goes off in a distant galaxy, for a few seconds, it can shine brighter in gamma rays than every other star in the entire observable universe put together. Billions of trillions of stars, outshone by a single dying object for about the length of time it takes to read this sentence aloud. Let me try to give that energy some shape. In a typical burst, a star releases in a matter of seconds roughly as much energy as our sun will radiate across its entire 10 billion year lifetime. All of it, the whole life output of a star, dumped out in one short scream of radiation. If that were spread evenly in every direction, it would be frightening enough. But that is not how a gamma ray burst works, and this is exactly where it turns into a weapon. A gamma-ray burst funnels its energy into two narrow jets, one blasting from each pole of the dying star, rather than spreading it out in a ball the way a supernova does. Think of a lighthouse instead of a bare bulb. Each jet is only a few degrees wide, a thin cone of annihilating radiation moving at very nearly the speed of light, which means the full horror of a gamma-ray burst is only ever felt by whatever happens to be standing directly in front of the barrel. There are two ways to make one, and both are grim. The long bursts, lasting from a couple of seconds up to a few minutes, come from the death of a truly enormous, fast-spinning star, larger even than the ones that become ordinary supernovae. Rather than leaving a neutron star, its core collapses straight into a black hole, and as it does, twin jets drill out through the body of the star and into space. We call these hypernovae, and they're the death of giants. The short bursts are, if anything, stranger. They last less than 2 seconds, and they come from the collision of two neutron stars, the ultra-dense corpses left behind by earlier supernovae. Two of these city-sized objects, each heavier than the sun, spiral around each other for eons, drawing closer and closer, until they finally slam together. In that instant, they merge into a black hole, or briefly into something even stranger, and they fire off a gamma-ray burst as they go. We actually caught one of these in the act back in 2017. Detectors on Earth felt the ripples in the fabric of space itself, gravitational waves from two neutron stars merging over 100 million light-years away, and then telescopes swung around and saw the flash they left behind. For the first time in history, we watched two dead stars collide and confirmed exactly what came out of it. Among other things, an absolute fortune in gold. There's a strange gift buried in that violence. When two neutron stars merge, the sheer force of it forges the heaviest elements in the universe, gold, platinum, uranium, and hurls them out into space. The gold in a wedding ring, the gold locked in every vault on Earth, was very likely made in a collision just like that one, long before the Earth existed. We were the debris of the most violent events in the cosmos on our fingers, and we call it precious. Now back to the barrel. Because a gamma-ray burst is beamed, whether it matters to you, comes down entirely to aim. If a burst goes off far away with its jet pointed somewhere else, we log it as an interesting flicker on our instruments and write a paper about it. If the jet is pointed at us, even from a great distance, it arrives as the brightest thing in the sky. And if one were ever to go off nearby, inside our own galaxy, with its jet lined up on the Earth, we would have a very serious problem indeed. How serious depends on distance, and the danger zone is frighteningly large. A gamma-ray burst aimed at the Earth from within a few thousand light-years, and that takes in an enormous swath of our own galaxy, could do real and lasting damage. The strange part is that the gamma rays themselves would never reach the ground. They would not need to. They would do their killing high up in the atmosphere, and then let the atmosphere finish the job for them. The mechanism is horribly elegant in its way. The blast of gamma rays slams into the upper air and rips apart the molecules of nitrogen and oxygen, cooking them into brown nitrogen oxides, the same chemistry you find in smog. Those compounds are ferociously good at destroying ozone. Within a matter of weeks, a gamma-ray burst could strip away a large fraction of the ozone layer across the entire planet, the invisible shield that keeps the sun's ultraviolet light from sterilizing the surface. With the shield gone, ordinary sunlight becomes a slow poison. Ultraviolet light pours down, killing the plankton at the base of the ocean food chain, scorching the plants, damaging every living thing exposed to the open sky. The brown haze high above may darken the world and drop the temperature, tipping the whole climate towards sudden freeze. A gamma-ray burst does not need to burn the Earth. It simply removes the one thing that ever made the Earth safe to live on. And there is real reason to suspect this has happened before. The second largest mass extinction in the history of life struck around 445 million years ago at the end of the Ordovician period, wiping out most of the species then alive. It came with signs of sudden cooling, and, tellingly, it hit the creatures living in the shallow, sunlit surface waters the hardest. Some scientists argue the cleanest explanation for that pattern is a gamma-ray burst that went off nearby and burned away the ozone. We cannot prove it, but the fingerprints fit uncomfortably well. What truly unsettles me about all this is the complete absence of warning. A gamma-ray burst travels at the speed of light, and so does any possible signal that it is coming. There is no early flash, no rumble, no telescope alert in advance. The light that tells you it happened is the very same light that does the killing. It would simply arrive on one perfectly ordinary day, and the first sign that a star had died and pointed its death at us would be the death itself, already here. So is there a gun pointed our way? Possibly. There is a star called WR104, around 8,000 light-years from here, that has given astronomers real pause. It is a rare, furious kind of star nearing the end of its life, spinning fast, exactly the sort that can produce a long gamma-ray burst. And when we first imaged it, it appeared to be turning almost face onto us, as though we were peering straight down the barrel of the jet it might one day fire. The good news, such as it is, arrives in two parts. Later observations hint that WR104 may be tilted further away from us than that first alarming image suggested, so we're probably not sitting directly in its line of fire. And a nearby gamma-ray burst aimed straight at the Earth is, by any honest reckoning, a rare event, something that might strike a given planet perhaps once in hundreds of millions of years. Rare, though, is not the same word as never. We have the geological scars to prove the difference. There is something uniquely bleak about this particular way to die. An asteroid you might deflect, a solar storm you might, at a stretch, prepare for. A gamma-ray burst is an execution with no trial and no appeal, delivered from a star so distant you may never once have seen it, a star that in truth died thousands of years before you were even born. The sentence was carried out long ago. The light is merely running late. If you want a single, pure example of how little the universe cares about us, this is it. A gamma-ray burst is not aimed with malice. It is not aimed at all. It is simply a jet of pure indifference sweeping across the galaxy, and the only thing that decides whether a living world lives or dies is whether it happened to be standing in the way. We survive, so far, on nothing more than the fact that space is very large and the beams are very thin. For all their terror, though, the supernova and the gamma-ray burst share one mercy. They come from far away, from stars we can at least point to and study from safe distance. The threats in this story have been creeping closer and quieter, and we are not finished with that descent. Because the stars themselves are not nailed to the sky. They wander, and right now, one of them is drifting toward us, slow and silent, on a course that will carry it into the outermost edge of our own solar system. Somewhere around 70,000 years ago, one of your ancestors may have looked up from a fire and noticed a faint red star that had not been there the night before, perhaps flaring for an evening or two before fading again. They could not possibly have understood what they were seeing. They were watching a passing star, another sun, drifting through the outermost fringe of our own solar system, closer than any star has come in the entire span of human existence. We call it Scholz's star, and it is a small, dim red dwarf traveling with an even smaller companion. About 70,000 years ago, it passed roughly 0.8 of a light year from the sun. That may still sound comfortably far away. It is not. It is well inside the Oort cloud, the great shell of comets we met a few chapters ago, which means an entire other star passed straight through the outer suburbs of our solar system, while our species was already walking the Earth. We only pieced this together recently, in 2015, when astronomers noticed something odd about the star. It was close, and yet it was barely moving across the sky, which usually means an object is heading almost straight toward you or straight away from you. Its motion showed it was leaving fast, and running the clock backward revealed where it had been. 70,000 years ago, it had brushed right past us, the closest known stellar encounter in our history, and we missed the live event by about 70 millennia. Scholz's star was small and quick, so it did little more than ripple the outer comet cloud as it went by. A gentle brush, not a blow, but it proved something important beyond any argument. The solar system is not a sealed and private place. It has an open door at the top, and other stars can and do wander in through it. And Scholz's star was only the most recent visitor. There's another one already on the way, and this one has our full attention. Its name is Gliese 710, and right now is a modest orange star about 62 light-years away, entirely unremarkable to look at, but it is heading almost directly for us. In roughly 1.33 million years, Gliese 710 will pass closer to the Sun than any star we know of, past or future. It will come near enough to plunge deep into the Oort cloud, far closer than Scholz's star ever managed, and settle briefly into our sky as one of the brightest stars in it. We know this with real confidence, and that itself is a quiet marvel. A European spacecraft called Gaia has spent years measuring the precise positions and motions of well over 1 billion stars, building a map of our corner of the galaxy in full motion. Feed that map forward in time, and you can watch the stars drift and see which ones are drawing close. Gliese 710 lit up as the standout, a slow-motion collision course still more than 1 million years shy of its closest approach. So what happens when a star plows through the Oort cloud? Not a direct hit on anything, almost certainly. The cloud is vast and mostly empty, and the odds of the star striking a particular comet, let alone a planet, are vanishingly small. The danger is gravitational. As the star passes, its gravity tugs on the loosely bound comets around it, nudging them out of their long, slow orbits. Some are flung outward, lost to interstellar space forever, and some are nudged inward toward the Sun, toward us. That inward nudge is the real threat, and it plays out with terrible patience. A close stellar pass can dislodge a whole swarm of comets and set them falling toward the inner solar system as a slow, drawn-out rain that can last 2 or 3 million years rather than a single sudden burst. Astronomers call it a comet shower. For that entire long stretch, the number of comets crossing the Earth's path climbs, and with it the odds that one of them is carrying our name. So the star itself is never the killer. Gliese 710 will pass and shine and move on, completely oblivious to us. The danger is what it leaves behind, a disturbed cloud slowly leaking comets into the space we live in, for ages after the star is gone. It is a threat with a fuse measured in millions of years, and the match may already have been struck by a star we cannot yet see clearly. Some of the comets that will menace our distant descendants may be receiving their first nudge right now. And passing stars are not even the main thing stirring the pot. The galaxy itself works on the Oort cloud constantly. As the Sun orbits the center of the Milky Way, the varying pull of all that distant matter, what astronomers call the galactic tide, gently kneads the outer comet cloud the entire time, endlessly reshuffling orbits and dribbling comets inward. The passing stars are the dramatic events. The galactic tide is the steady, patient hand working behind the scenes. Put those two together and the picture shifts. The Oort cloud is not a still and frozen reservoir sitting quietly at the edge of the solar system. It is being stirred always slowly by the galaxy, and now and then violently by a passing star, and every so often it spills. The comets we see are the drips from a container that is being carried, jostled, across a crowded and moving galaxy, and we happen to live directly beneath it. This idea that something out in the dark periodically shakes comets loose and pelts the Earth led to one of the strangest hypotheses in modern science. In the 1980s, some researchers thought they saw a pattern in the fossil record, mass extinctions arriving in a rough rhythm, roughly every 26 million years. Something they reasoned, had to be triggering comet showers on a schedule. And so they proposed a genuinely chilling culprit. They called it Nemesis. The idea was that the sun might have a hidden companion, a faint and distant star, a red or brown dwarf, riding a vast looping orbit lasting tens of millions of years. Each time it swung closest, the thinking went it would tear through the Oort cloud and rain comets down on the inner planets, and the fossil record would dutifully record the slaughter. A Death Star, quite literally, bound to our own sun, coming around again and again like clockwork. It was a wonderful, terrifying idea, and it appears to be wrong. Astronomers went hunting hard for Nemesis, and a sweeping infrared survey of the whole sky, sensitive enough to spot even a cold, dim companion out to great distances, turned up nothing of the kind. The supposed 26 million year rhythm in the extinctions looks shakier the more carefully people examine it. As far as we can tell, the sun travels alone. There is no Death Star tethered to us after all. But the unsettling core of the idea did not die with it. A nemesis on a fixed, ticking schedule may not exist. The wandering stars and the comet showers they trigger in their wake absolutely do. The threat is entirely real. It simply is not punctual. It arrives on the galaxy's own irregular timetable whenever a star happens to drift too close, which over the long life of the solar system is often enough to matter a great deal. There is a second, related worry that comes from our journey through the galaxy. The sun does not orbit the Milky Way in a flat, tidy circle. It bobs gently up and down through the crowded central plane of the galaxy, like a horse on a carousel, crossing that dense midline every 30 million years or so. Some researchers suspect those crossings, through regions thick with gas clouds and stars, may line up with disturbances in the comet cloud and pulses of impacts. The evidence is argued over. The motion itself is not. What all of this adds up to is a quiet correction to how we picture our home. We like to imagine the solar system as a neat, self-contained little machine, the planets going round and round, safe inside their own walls. But there are no walls. The sun is a moving object in a moving crowd, and the crowd reaches in. Comets fall because stars drift by, because the galaxy tugs, because we are one small part of something vast and busy that pays us no mind whatsoever. Still, a passing star is, in the end, a threat we can see coming. Gliese 710 announced itself more than 1 million years ahead of time. We can point to it, measure it, and predict almost to the century when it will arrive. That is a strange kind of comfort, but it is comfort of a sort. The universe, just this once, has laid its hand on the table well in advance. So let me take even that comfort away. Everything we have talked about so far, the asteroids, the comets, the passing stars, the exploding suns, all of it shines or reflects or announces itself somehow to a patient enough watcher. We can, in principle, see them coming. But the galaxy also holds things that give off no light at all. Objects that drift through the dark utterly unseen, that we could not detect even if one were bearing straight down on us. And some of them are far more dangerous than any star. Picture an object with a mass of 10 suns, moving silently between the stars, radiating nothing, reflecting nothing, swallowing even the light that falls onto it. No telescope could pick it out against the black. It could be a single light year away, closing on the solar system, and we would have no clue until the planets themselves began to move in ways they simply should not. There are wanderers out there in the dark with no face and no warning, and that is exactly where we're going next. On the 19th of October, 2017, a telescope in Hawaii caught a faint dot of light moving through the solar system on a very strange path. It was not orbiting the sun the way everything local does. It had come in fast from above the plane of the planets, whipped around the sun, and was already on its way back out, never to return. It was the first object we had ever confirmed from another star system, a genuine interstellar visitor, and we caught it only as it was leaving. We named it Oumuamua, a Hawaiian word for a scout, a messenger that arrives first. It was small, a few hundred meters long, oddly elongated, and tumbling end over end. It behaved strangely enough that a few serious people briefly wondered out loud whether it was natural at all, though the evidence points to a peculiar shard of rock or ice. Whatever it was, it had been drifting between the stars for who knows how many millions of years before it happened to pass through our neighborhood. 2 years later, in 2019, we caught another one, a comet this time, unmistakably from beyond the solar system, which we named Borisov. 2 interstellar visitors inside 2 years, once we finally had the eyes to notice them. And that tells you something quietly staggering. The space between the stars, which we like to picture as a clean and empty void, is in fact littered with drifting debris, the cast-offs of other star systems, wandering alone through the dark. And most of it we will never see at all. Because to be spotted at all, an object has to do us the courtesy of coming close and catching the sunlight. The ones that pass at a distance, or that give off no light of their own, slip through completely unnoticed. And once you start thinking seriously about what might be out there in the unlit dark, drifting on its own between the stars, the possibilities get a great deal more frightening than a tumbling shard of rock. Start with the rogue planets. When solar systems form, they're chaotic, violent places, and not every world that forms gets to keep its home. Some are flung outward by the gravity of their larger siblings, slingshot clean out of their birth system and into the dark between the stars. These are free, floating planets, entire worlds, some the size of Jupiter, wandering the galaxy with no sun to orbit, no light, no warmth. And there may well be more of them than there are stars. Let that settle for a moment. There could be billions, even trillions of starless planets drifting through our galaxy, cold and dark and effectively invisible. We only know they exist because, very occasionally, one passes directly in front of a distant star, and its gravity briefly bends and brightens that star's light, a tiny flicker that betrays a world we could never otherwise detect. For every one we happen to catch in that act, countless others slip by entirely unseen. A rogue planet drifting into the solar system would be bad, though probably not the end of us, unless it passed very close. Its main effect would be gravitational, tugging at the orbits of the planets, nudging the delicate clockwork of the solar system a little out of true. But a rogue planet is a lightweight next to the thing I actually want to talk about, because the same dark that hides wandering worlds also hides something with the mass of an entire star crushed down into almost nothing. A rogue black hole. When a truly massive star dies and its core collapses, it can leave behind a black hole, a knot of gravity so extreme that not even light can climb back out of it. Usually these are born in pairs or clusters, but plenty end up alone, kicked loose by the violence of their own creation, drifting through the galaxy in perfect silence. A dead star's heart, a few dozen times the mass of the sun, packed into a sphere you could tuck inside a city, and black as the space it moves through. Black holes are not the only dead stars adrift out there. Their slightly smaller cousins, neutron stars, are just as dark and nearly as dense, the crushed cores of exploded giants, a whole sun's worth of matter squeezed into a ball the width of a city. Most have long since cooled too far to shine. They too drift through the galaxy in their millions, silent and heavy. The graveyard of dead stars is not tidy, and it is certainly not empty. It is all around us in the dark, quietly moving. Nobody knows exactly how many are out there, and the estimates are not comforting. Our galaxy may hold somewhere around 100 million of these isolated black holes, perhaps far more, threaded invisibly through the same space that holds the stars. They emit nothing. They reflect nothing. Unless one happens to be actively swallowing gas and glowing as it does, a lone black hole is, for every practical purpose, completely undetectable. It is the darkest thing in an already dark sky. For a long time, that made them almost impossible to prove. Then, in 2022, astronomers finally pinned one down. They watched a distant star appear to shift and brighten in a very particular way, over several years, as something massive and invisible drifted in front of it and bent its light. When they ran the numbers, the unseen object came out at around 7 times the mass of the Sun, roughly 5,000 light-years away, wandering the galaxy entirely on its own. The first rogue black hole ever confirmed, found purely by the shadow it cast in starlight. Now think about what one of these would do if it wandered toward us. It would not need to hit anything. It would not even need to come especially near the Earth. Simply passing through the outer solar system, that immense invisible mass would take hold of the planet's orbits and begin to pull them apart. The careful gravitational balance that has kept the Earth in its narrow, life-friendly lane for billions of years will be shrugged aside in a matter of a few years. The outcomes are all bad in their own different ways. The Earth might be swung in closer to the Sun and slowly roasted. It might be flung outward into the deep cold. Or, in the worst version, it might be torn away from the Sun altogether and cast out into interstellar space, carrying us with it. Our planet would become exactly the kind of thing we have just been describing. A rogue world, dark and freezing, wandering the galaxy with no star to call its own. Picture that Earth. Cut loose from the Sun, it would fall dark within days. Within weeks, the surface would plunge toward the cold of deep space, hundreds of degrees below freezing. The oceans would ice over, and then the air itself would begin to snow out of the sky, settling as drifts of frozen oxygen and nitrogen on the ground. Anything living on the surface would be long dead, and the whole frozen ball would sail on into the black, no longer part of any solar system, just another silent wanderer in the dark. And if we ever strayed close to the black hole itself, close enough to feel it directly, the death would be stranger still. The pull of gravity drops off sharply with distance. So near a black hole, your feet would be yanked far harder than your head. You would be stretched, drawn out into a long, thin thread of matter, in a process astronomers have named, with typically grim humor, spaghettification. The Earth, and everyone on it, pulled into a fine stream and poured over the edge into the dark. The truly chilling thing about a rogue black hole is not its power. We have met powerful things already in this story. It is the total silence of it. There would be no bright approaching light, no comet hanging in the sky, no star slowly swelling, none of the warnings that even our worst threats usually grant us. The first sign that anything was wrong would be the other planets beginning to drift, the seasons quietly failing, the whole sky slowly rearranging itself. By the time we understood, it would already be far too late. This is the perfect predator in its way. It hunts without eyes and without intent, of course, but the effect is the same. It gives off no light, throws no shadow you could catch in time, makes no sound, follows no schedule. It simply drifts, blind and silent and immensely heavy, through a galaxy that holds millions of its kind, and every so often, by pure chance, one of them drifts towards something alive. We survive, once again, only because the galaxy is so vast that even 100 million killers can rattle around inside it and mostly miss. Over the 4.5 billion years the solar system has existed, we have almost certainly had close calls we know absolutely nothing about, and over the billions of years still to come, the dice will keep on rolling. It is not a question of whether wandering masses drift near us. They do, on the galaxy's slow and patient clock. It is only a question of how close and how unlucky, and whether anything is still here to notice when the worst of them arrives. And this is the part that reframes everything. A single rogue black hole is a stray, a piece of stellar wreckage kicked loose and left to wander. But not all black holes are strays. Some of them stayed exactly where the action is. And the largest of all sits at the very center of our galaxy, on a throne of gravity, with the entire Milky Way, every star, every world, every one of those rogue wanderers, and you wheeling slowly around it. You cannot see it from where you sit, because thick clouds of dust and hundreds of billions of stars stand between us and the core. But it is there, 26,000 light years away, in the direction of the constellation Sagittarius. It weighs about 4 million times as much as the Sun. And for a long time, we could only infer it, the way we once inferred the Oort cloud from the behavior of the things around it. Until, at last, we found a way to watch it directly. Right now, as you read this, you are moving. The Earth is carrying you around the Sun, and the Sun is carrying all of us in a great slow circle around something 26,000 light years away. It takes the Sun about 230 million years to complete a single lap. The last time we were on this side of the galaxy, the dinosaurs had not yet appeared, and the thing we are all circling, the anchor of that immense orbit, is a hole in space 4 million times heavier than the Sun. It is called Sagittarius A star, and it is the supermassive black hole at the heart of the Milky Way. Every one of the galaxy's few hundred billion stars, ours included, is bound in orbit around the center where it sits. You cannot see it. Between us and the core lie thick lanes of dust and gas and uncountable stars, hiding the galactic center behind a veil. For most of history, we did not even know it was there. Working out that it took one of the great detective efforts in all of modern astronomy. The trick was to watch the stars closest to the center, the ones whipping around whatever lurks there. Two teams, one led by Andrea Ghez and one by Reinhard Genzel, spent decades patiently tracking a handful of stars near the core, night after night, year after year. And those stars were not drifting lazily along. They were racing on tight, looping orbits around a single point of empty-looking space, as though held by something enormous that gave off no light whatsoever. One star in particular, known as S2, told the whole story. It swings around the galactic center on an orbit lasting about 16 years, and at its closest approach, it whips past that invisible point at something like 7,000 kilometers a second, more than 2% of the speed of light. For a star to move like that, held so tightly on so short a leash, the thing at the focus of its orbit had to be unthinkably massive and unthinkably compact. There was only one thing it could possibly be. For a million times the mass of the Sun, crammed into a region smaller than the orbits of our own inner planets. Nothing but a black hole can be that heavy and that small at once. The work was so decisive that Ghez and Genzel shared the Nobel Prize in Physics for it in 2020. We had proven, past reasonable doubt, that a monster sits at the center of our galaxy, and that we have been quietly orbiting it the entire time. Then, in 2022, we did something that still amazes me. A network of telescopes spread across the whole of the Earth, working together as one instrument the size of the planet, managed to take its picture, not the black hole itself, which by its very nature gives off no light, but its silhouette, a dark circle ringed by the glow of superheated gas swirling just outside the point of no return. We had photographed the shadow of the thing at the center of the galaxy, the unseeable at last seen. For now, thankfully, our monster is sleeping. Sagittarius A star is quiet, feeding only on the occasional stray wisp of gas, giving off surprisingly little for its enormous size. If you could somehow stand at a safe remove from it today, it would be a strangely dark and calm place, a great mass wrapped in silence. But supermassive black holes are not always so restrained. When one of them begins to eat in earnest, it becomes the most violent and most luminous kind of object in the entire universe. We call them quasars. A quasar is a supermassive black hole caught in the act of feeding, and it is a genuinely staggering thing. As gas and dust and shredded stars spiral inward, they pile up into a disk, compressed and heated to millions of degrees, until that disk blazes brighter than every star in the surrounding galaxy put together. From clear across the universe, some of the brightest points of light we can find are not galaxies at all. They are single black holes eating. And a feeding black hole does far more than shine. The infalling matter, twisted by ferocious magnetic fields, launches twin jets of radiation and particles out from its poles at nearly the speed of light, punching thousands of light years out into space. A quasar is a black hole turned into a weapon on a galactic scale, flooding everything around it with hard radiation. Any living world caught too close to one when it switched on would simply be scoured clean of life. So consider the uncomfortable thought. Our black hole is quiet now. It has not always been, and will not always be. All it takes is a large enough cloud of gas, or an unlucky star, to wander too close and be captured, and the monster at the center wakes and begins to feed. When that happens, the calm dark heart of the galaxy flares into something that pours radiation out across the surrounding thousands of light years. We even have evidence that it has stirred in the fairly recent past. Reaching out above and below the center of the galaxy are two colossal bubbles of high-energy particles, each stretching some 25,000 light years into space, like enormous wings. We call them the Fermi bubbles, and the leading explanation is that they were blown outward by an eruption from our central black hole a few million years ago. The monster rolled over in its sleep and left marks the size of the galaxy. There are hints of something more recent still. Certain clouds of gas near the galactic center appear to be glowing with a kind of light echo, an afterglow from flare that seems to have gone off only a few hundred years ago, around the time humans were building tall sailing ships. Our black hole may have flickered awake within recorded human history, briefly, and we never knew because all of it was hidden behind the dust. The giant is not sleeping quite as soundly as we would like to believe. And then it reminds us exactly what it can do to anything that strays too near. Astronomers have watched, in other galaxies and glimpsed in our own, what happens when a whole star wanders too close to a supermassive black hole. The star is stretched, torn apart, and half of it is devoured in a brilliant flare that can outshine everything around it for months on end. These are called tidal disruption events, and they are quite simply a black hole catching and eating a star in full view of our telescopes. We, at least, are a long way from all of this. Our sun sits about 26,000 light years out from the center, in a quiet stretch of one of the galaxy's spiral arms, while clear the crowded, violent core. If Sagittarius, a star, woke tomorrow and blazed into a quasar, we are probably far enough out to weather it. Probably. It is worth noticing by now how often that one word has to do the heavy lifting in this story. But step back and look at the whole arrangement, because this is where it stops being about us at all. Ours is not a special case. Nearly every large galaxy in the universe has one of these supermassive black holes anchored at its center, millions or even billions of times the mass of the sun. They are not rare accidents. They are a standard feature, the dark hearts around which entire galaxies are built. Stranger still, the black hole and its galaxy seem to grow up together. The mass of the central black hole tracks the properties of the galaxy around it so closely that the two must be bound deeply together, feeding and shaping one another across billions of years. The monster did not simply move into the galaxy after the fact. In some real and literal sense, the galaxy grew up around the monster. The darkness came first, and the light arranged itself around it. That is the thought I cannot shake, standing here in the middle of the story. We tend to imagine the universe as a place of stars and worlds, with the dark as mere background, the empty space between the interesting things. But it is very nearly the other way around. The organizing centers of the great structures of the cosmos, the anchors that hold the galaxies together, are these vast wells of nothing into which everything, given enough time, tends to fall. And that changes the kind of story this is. For 9 chapters, we have been asking a very human question. What could reach out of space and end us? The asteroid, the flare, the burst, the wandering dark. But standing here at the dead center of the galaxy, staring at the thing we all orbit, a colder and much larger question starts to take over. It is no longer only about our own survival. It is about whether survival, anywhere, is even the normal outcome. Because if the galaxy is like this dust and fire and radiation, riddled with invisible black holes, crossed by killer beams, organized around a monster at its heart, then a living world is a fragile, unlikely thing, balanced for a little while in a narrow, safe zone inside a fundamentally hostile place. And a galaxy this dangerous should have consequences. It should leave evidence. Specifically, it should leave a very particular kind of silence. Look up at the sheer number of stars, the hundreds of billions in our galaxy alone, most of them older than the sun, many with worlds of their own. By all rights, the sky should be crowded with others, with signals, with voices, with the faint glow of distant civilizations going about their business. Instead, when we point our instruments outward and listen with everything we have, we hear nothing at all. Just a vast, patient, unbroken silence. And after everything we have just seen, that silence starts to feel less like an accident and more like an answer. In 1950, over lunch at the Los Alamos laboratory, a group of physicists were chatting idly about flying saucers and the chance of life among the stars. The talk drifted on to other things. And then, out of nowhere, in the middle of the meal, one of them, Enrico Fermi, one of the sharpest minds of the century, suddenly asked a simple question that has haunted science ever since. Where's everybody? The table went quiet, because once you really think about it, there's no good answer. On its face, it sounds like an odd thing to be troubled by, but Fermi was doing what he did best, running the numbers in his head. And those numbers are genuinely disturbing. Our galaxy holds a few 100 billion stars. A large fraction of them have planets. Many of those planets sit in the comfortable zone where liquid water, and therefore life as we know it, could exist. And the galaxy itself is not young. It is well over 10 billion years old. Think about what that head start really means. The Earth is a relative latecomer. There are stars and worlds in our galaxy billions of years older than the Sun, which means any life that arose on them had a billion-year running start on us, sometimes several. If even one of them had produced a curious, tool-making species like ours, they would have had almost unimaginable stretches of time to do something with it. And a little time goes a very long way. Consider what spreading out would actually take. Even without any magic, without travel faster than light, a determined civilization could cross the entire galaxy in a few million years, send out ships that build more ships, hop from star to star, and the wave spreads outward on its own. A few million years sounds enormous to us, but set against the age of the galaxy, it is the blink of an eye. Any civilization with a head start of even a fraction of that should already be everywhere. The galaxy should be full. So it should be crowded. By every reasonable calculation, the Milky Way ought to be a busy place, dotted with settled worlds, humming with radio chatter, marked here and there by the engineering of species far older than ours. When we look up, we should see evidence everywhere. Instead, we see a sky that appears, as far as we can tell, completely untouched. Natural, empty of anyone. That gap between what should be and what actually is has a name. The Fermi paradox. People have tried to put arithmetic to it. In 1961, an astronomer named Frank Drake wrote down a now famous equation, a string of factors multiplied together, meant to estimate how many communicating civilizations should exist in our galaxy right now. How many stars, how many with planets, how many planets fit for life, how often life turns intelligent, and on down the line. Depending on your guesses, the answer swings from millions of civilizations all the way down to a single lonely, echoing one. For decades, the optimists have been listening. Radio telescopes have swept the sky for any whisper of an artificial signal, any hint of a broadcast leaking from another world. It is one of the most quietly hopeful things our species has ever done, sitting patiently with an ear pressed to the cosmos, waiting for someone, anyone, to say something at all. And in all that time, across all that listening, we have heard essentially nothing. There was one tantalizing moment. In 1977, a radio telescope in Ohio picked up a strong, strange signal coming from the direction of Sagittarius. So striking that the astronomer reviewing the printout circled it and scrawled a single word in the margin. Wow, it lasted 72 seconds, and it never came again, no matter how hard or how long anyone searched for it. One shout in half a century of listening, and we cannot even be certain it was them. Otherwise, silence. So we are left holding the paradox in its full, uncomfortable weight. The universe looks perfectly suited to producing life. It has had more than enough time. It is unthinkably large. Every ingredient for a galaxy teeming with civilizations appears to be present and accounted for. And yet, when we look and listen and search, we find no one. Something is wrong with one of our assumptions. The only question is which one, and each of the possible answers carries its own particular dread. The gentlest answer is that we are simply rare, that the chain of lucky accidents needed to get from a lifeless rock to a thinking creature is so long and so improbable that it almost never runs all the way to the end. Life might start easily enough, but the leap to complex life and then to intelligence may be a series of near miracles that most worlds never manage. Under this reading, the silence is not sinister at all. We are just extraordinarily lucky and extraordinarily alone. And the list of things that had to go right for us is genuinely sobering. A stable star that does not flare too violently. A planet at just the right distance for liquid water. A large moon to steady our tilt and calm the seasons. A magnetic field to hold off the solar wind. Plate tectonics to keep recycling the surface. The right giant planets in the right places to sweep away some of the debris. And then, on top of all of it, the long, fragile, easily broken climb of evolution itself. A second answer is stranger and, in its way, almost cheerful. Perhaps the silence has nothing to do with life being rare. Perhaps we are alone because we are early. The universe is still young, only a little over 13 billion years into a lifespan that will run for trillions. Most of the stars that will ever exist have not yet even been born. It could be that the great age of galactic civilizations is still ahead of us, and we are among the very first guests to arrive at a party that has barely begun. But there is a third answer, and it is the one that keeps people awake at night. It goes by the name of the Great Filter. The idea is that somewhere along the enormous road from lifeless chemistry to a galaxy-spanning civilization, there's a step, at least one, that is very nearly impossible to pass. A wall, a filter that stops almost everything before it can reach the stage of spreading among the stars. And the crucial, terrifying question is where exactly that wall sits. If the Great Filter lies behind us, we can breathe a little easier. It would mean the hardest part is already done. Maybe the origin of life itself is the near impossible step, or the jump to complex cells, or the dawn of intelligence. And we are the astonishingly rare world that made it through. In that case, the silence is simply the sound of how few ever get this far. And our survival, so far, is a kind of miracle we would be fools to waste. But if the Great Filter lies ahead of us, that is a very different story. It would mean the hard step, the one that stops almost everyone, is not behind us at all. It is still coming. It would mean that countless civilizations before us climbed to roughly where we stand now, full of promise, reaching for the stars, and then hit something that reliably ends them every single time. And that we are walking toward the same wall in the dark with no idea how close it is. So what could it be, this filter waiting up ahead? The obvious first suspect is us. A civilization clever enough to spread across the stars is also, by then, clever enough to destroy itself. Nuclear weapons, engineered plagues, runaway changes to its own climate, technologies it builds but cannot control. Perhaps intelligence, past a certain point, simply tends to burn itself out, and every promising species snuffs its own candle before it can leave home. Or perhaps the filter is not anything civilizations do to themselves. Perhaps it is exactly the kind of thing this whole film has been about. Look back over what we have already seen. Impacts, gamma-ray bursts, nearby stars that explode, wandering black holes, a galaxy that is, on the whole, a hostile and violent place. Maybe life arises again and again across the cosmos, and again the sky simply resets it, wiping the slate clean before anyone can get far enough out to be heard. And there is a colder possibility still. Perhaps they are out there, and they are silent on purpose. Some thinkers have imagined the galaxy as a dark forest, full of others who have all learned the same brutal lesson. That in a universe where you can never truly know a stranger's intentions, the safest thing to do is stay hidden, say nothing, and quietly destroy anything that reveals itself. If that is true, then our cheerful decades of broadcasting our existence to the stars may turn out to be the most dangerous thing we have ever done. I do not know which of these is right. Nobody does. But I find it impossible to sit with everything we have seen in this story and not feel the silence pressing in. A universe this vast, this old, this apparently welcoming to life, and yet not one clear voice anywhere in it. Whatever the reason turns out to be, the message underneath is the same. Surviving out here, over the long haul, may be far rarer and far harder than we would ever like to admit. Whatever is keeping the galaxy quiet, our situation for now is plain enough. We are on our own, one species on one small world, circling one ordinary star in one arm of one galaxy, with no help coming and no one answering. And even that galaxy, the great wheel of stars we call home, is not the fixed and permanent thing it appears to be, because something enormous is already moving toward it. Something you can see with your own eyes on a clear enough night, if you only know where to look. Find a truly dark sky, far from any city, on a clear autumn night, and look toward the constellation Andromeda. With a little patience, you may pick out a faint, fuzzy smudge, barely brighter than the darkness around it. Most people who notice it have no idea what they are looking at. That smudge is the single most distant thing the human eye can see without any help at all. And it is a whole galaxy coming straight for us. It is called the Andromeda Galaxy, and it is our nearest large neighbor in the cosmos. It holds something like 1 trillion stars, which makes it even bigger than our own Milky Way, and it sits about 2.5 million light years away. It is so far off that the light entering your eye tonight left it 2.5 million years ago, back when our ancestors were not yet quite human. You are quite literally looking into the deep past. For a long time, we did not even realize such things existed. Astronomers called these faint smudges nebulae and assumed they were clouds of gas inside our own galaxy. It was only about a century ago, when Edwin Hubble measured the distance to Andromeda, that we grasped the shattering truth. It lay far beyond the Milky Way. It was a separate island of stars entirely, one of countless others, and the universe was suddenly a great deal larger and lonelier than anyone had dared to imagine. Now, most galaxies across the universe are rushing away from us, carried apart by the expansion of space. Andromeda is one of the rare exceptions. When we split its light apart and read it, the colors are shifted in a way that tells us it is not receding from us at all. It is approaching, falling toward us through the dark at around 110 kilometers a second, drawn by the mutual gravity between two giant galaxies that have been circling a slow embrace for billions of years. Run that motion forward, and the conclusion is unavoidable. In roughly 4 billion years, the Andromeda Galaxy and the Milky Way are going to collide. Two great wheels of hundreds of billions of stars each, drawn together, will crash through one another and, over the ages that follow, merge into a single new galaxy. It is one of the largest scale catastrophes we can actually see coming, written plainly in the light of smudge you can pick out with your naked eye tonight. And yet the word collision is misleading in a way that reveals just how empty space truly is. When these two galaxies crash together, almost none of their stars will actually strike each other. Not 1 in a million. The chance of our sun hitting another star in the entire violent merger is, for all practical purposes, 0. Because for all their hundreds of billions of stars, galaxies are mostly, overwhelmingly, empty space. Let me put that emptiness in scale. If the sun were a single grain of sand, the nearest other grain, the next star over, would be a few kilometers away, with nothing but void in between. Now take two enormous clouds of such grains, each spread across whole kilometers, and pass them straight through each other. The grains sail past one another untouched, waving as they go. That is a galactic collision, titanic and strangely intimate, and almost entirely without impact in the literal sense. What does collide as the gas? Galaxies are threaded through with vast clouds of gas and dust, and when the two galaxies meet, those clouds slam into each other and compress. And compressed gas is exactly what makes new stars. So the merger will light up in a furious burst of star birth, whole nurseries of brilliant new suns igniting at once. A galaxy briefly blazing with fresh light, even as it is torn apart and remade. The gravity, meanwhile, will make a spectacular ruin of both galaxies. The elegant spiral arms of the Milky Way, the shape we have drawn in every textbook, will be pulled and stretched and flung out into long streamers of stars, tidal tails reaching millions of light years into the dark. Order dissolves into chaos. The familiar pinwheel unwinds. Two of the most beautiful structures in our corner of the universe come apart at the seams over hundreds of millions of years. And where is the sun in all of this? Nobody can say for certain, but the odds are that our star, or whatever is left of it by then, gets thrown into a wildly new orbit. It might be flung far out into the sparse outskirts of the merged galaxy, or slung inward toward the chaotic center. If any eyes remain on any world around it, they would find themselves somewhere utterly unfamiliar, under a completely rearranged sky. There is a grim timing to all of this, though. For a billion years from now is almost exactly when the sun will be entering its own death throes, swelling toward the red giant we met earlier. So by the time the two galaxies truly collide, the Earth, if it exists at all, will very likely be a scorched and lifeless rock already. The Great Collision may well play out over a dead planet, with no one left on it to look up and watch the sky catch fire. But imagine, for a moment, that someone is there to see it. Over hundreds of millions of years, that faint smudge in the constellation Andromeda would slowly grow, first into a clear disk, then into a great glowing spiral hanging in the night, larger than the moon, then larger than a fist held at arm's length, then dominating the entire sky. A second galaxy, filling the night, sliding closer year by year with terrible, silent patience. Then the two would pass through each other. The sky would blaze with the light of new stars born in the collision, ribbons of stars torn loose and flung across the dark, the two galactic centers swinging past one another like slow dancers. And that would not be the end of it. Galaxies in a merger do not simply stop. They swing apart, still held by gravity, and fall back together and pass through again and again over billions of years until at last they settle. What settles, in the end, is something entirely new. The two grand spirals, the Milky Way and Andromeda, will be gone, their elegant structure erased forever. In their place will sit a single vast, formless ball of stars, an elliptical galaxy, dim and old and smooth. Astronomers have already given this future object a name, half in jest. They call it Andromeda. It is our home and our neighbor, fused into one and utterly unrecognizable. And deep in the heart of that new galaxy, two monsters will meet. Our own central black hole, Sagittarius A star, and the even larger one lurking at the core of Andromeda, will be drawn together as the galaxies merge. They will circle each other closer and closer, radiating ripples in space-time as they go, until finally they collide and merge into a single, even more enormous black hole. A wedding of monsters, felt as gravitational waves across the whole universe. There is something almost peaceful about this particular catastrophe, and that unsettles me more than the violent ones do. Nothing screams, nothing burns in agony. Two of the largest structures in the local universe are utterly destroyed, unmade as the things they were, and yet across the whole grand collision, scarcely a single star is harmed. It is destruction as pure transformation, so vast and so slow that from inside it, it would look less like an ending and more like a strange and beautiful sky. Nor does it stop with Andromeda. The Milky Way and Andromeda are only the two giants of a small family of galaxies, dozens of them bound together by gravity into what we call the local group. Over the long, deep future, gravity will draw that whole family inward. One by one, the galaxies of the local group will fall together and merge, until all that remains is a single enormous island of stars, standing alone in the dark. And that word alone is the one to hold on to. Because while our little group of galaxies pulls itself together, everything else in the universe is doing the opposite. Every other galaxy, every distant cluster, all the countless islands of light beyond our own family, are racing away from us and racing faster with every passing age. The universe is expanding, and worse, that expansion is accelerating, driven by something we barely understand at all. So even the largest things we know, the galaxies themselves, are temporary. They collide, they merge, they are flung apart, they die. Up to this point, every thread in this story has at least been a thing. A rock you could weigh, a star you could name, a black hole you could, in principle, point to. Frightening, yes, but solid, real, made of honest matter with an address somewhere in space. But we are about to leave the world of things behind. The deepest dangers of all are not objects floating within the universe. They are hidden in the rules that run it, in the fine print of physics, in the very stability of empty space and the fabric of reality itself. And if there's a flaw down there, in the foundations, then it does not matter how far you run or where you try to hide, because the ground of reality would be failing everywhere all at once. There is a thought that genuinely frightens some of the most level-headed physicists alive. What if empty space, the plain nothing between the stars, is not actually stable? What if the entire universe is like a ball resting in a shallow valley, sitting quietly, looking perfectly settled, while just over the ridge there's a far deeper valley it could tumble into at any moment? And what if that fall, once it began, could never be stopped? To understand the fear, you first have to unlearn something. In physics, a vacuum is not nothing. Empty space is filled everywhere with invisible fields, a kind of restless quantum sea, and those fields carry energy even when not a single particle is around. What we call empty space is really just the lowest energy state those fields have managed to settle into, the floor of the valley, and the whole of reality is built on top of that floor. One of those fields is the reason you exist in the form you do. It is called the Higgs field, and it fills all of space, and as particles move through it, they draw their mass from it. It was confirmed in 2012 when physicists finally detected its associated particle, the Higgs boson, deep in the collisions of a giant machine buried beneath the border of France and Switzerland. That discovery was a triumph. It also handed us a deeply unsettling number. Picture the energy of the vacuum as a landscape of hills and valleys. Our universe is sitting in one of the low points, and for all of history we assumed it was the lowest point, there was the true and final floor. But there may be more to the landscape than that. We might be resting in a shallow dip partway down the slope, comfortable, apparently stable, and yet not truly at the bottom at all. Physicists have a name for a spot like that: a false vacuum. The difference matters enormously. If we sit in the true vacuum, the real floor, then reality is stable and there's nothing to fear from this direction. If instead we sit in a false vacuum, then our entire universe is only metastable, balanced in a dip, and given enough time it can find a way over the ridge and drop into the deeper valley below. And when a universe does that, it does not do it gently. And this is where the unsettling number comes in. When physicists take the measured mass of the Higgs boson, together with the mass of the heaviest known particle, the top quark, and feed them into the equations, the answer that comes back is not a clean, comforting stable. It sits almost exactly on the knife's edge between stable and unstable, leaning, if anything, toward the wrong side. As far as our best current physics can tell, our vacuum may well be false. So suppose it is. What actually happens then? It would begin somewhere, anywhere, with a single random quantum event, the same kind of chance flicker that rules the subatomic world. In one tiny patch of space, the vacuum tunnels through the ridge and drops into the true, deeper state. And there, a bubble is born, a bubble of true vacuum, of a realer reality sitting inside our own. And that bubble immediately begins to grow. It grows fast. The wall of the bubble races outward at very nearly the speed of light, a shell of transition sweeping through space, converting everything it touches from our vacuum into the deeper one. Nothing can outrun it, because nothing travels faster than light. And the wall carries a colossal amount of energy, released as our comfortable false vacuum drops to the true one, so the boundary itself becomes a shell of annihilating force. But the energy is almost beside the point. The real horror is what waits inside the bubble. In there, the vacuum is different, which means the fields are different, which means the fundamental constants of physics are different. The strengths of the forces, the masses of the particles, the rules that let atoms hold together and chemistry happen and matter exist at all. Inside the bubble, those rules are rewritten and almost certainly rewritten into a form where nothing like us, nothing like anything, can exist. So this is not destruction in any way we normally mean the word. A supernova burns you. A black hole crushes you. Vacuum decay does something stranger and more absolute than either. It replaces the reality you are made of with a different one, in which the very concept of you has no meaning. It does not so much kill the universe as swap it out for another, and the old one, our one, simply ceases to have ever been possible. And there's a kind of mercy in it, if you can even call it that. You would never know. The bubble wall travels at the speed of light, and so does every signal, every photon, every possible warning it could ever give. There is no flash on the horizon, no shimmer in the sky, no moment of dawning realization. The wall arrives at the same instant as the first hint of its existence. One moment you're here. The next, there is no here and no you and no next. There would be no pain, because pain takes time and nerves and a working brain, and all of those would be gone faster than any signal could cross them. There would be no fear, because fear needs a future to be afraid of. The transition would pass through you more quickly than a single thought could form. In a very real sense, you would not die. You would simply instantaneously never have been able to be there in the first place. I want to be clear that this is not fringe speculation or science fiction. The mathematics of vacuum decay was worked out carefully back in 1980 by the physicists Sidney Coleman and Frank DeLucia, and it has been refined and taken seriously ever since. It falls straight out of the same quantum field theory that gives us the most precise and successful predictions in all of science. This is not somebody's nightmare. It is a line item in the physics. Now for the reassurance, because there genuinely is some. If the vacuum could be tipped over easily by ordinary violent events, it would have happened already. Nature runs experiments far more energetic than anything we can build. Cosmic rays, single particles moving at ferocious speeds, have been slamming into things all across the universe for billions of years, at energies our own machines cannot come close to. And the universe is still here. So whatever it takes to trigger this, it plainly is not easy. The spontaneous version, the pure random quantum tunneling, is also thought to be staggeringly unlikely on any human timescale. The expected wait for it to happen on its own is a number so vast, it makes the current age of the universe look like nothing at all. By that measure, vacuum decay is not something to lose sleep over tonight, or this millennium, or across a genuinely mind-bending stretch of time to come. And yet, the universe is a very large place, and a bubble only has to begin once, somewhere, to matter. It could nucleate spontaneously in some distant region, far across the cosmos and start its silent expansion at the speed of light. If it did, we would have no way of knowing, no signal running ahead of it to warn us. For all anyone can prove, a wall of true vacuum could already be out there, sweeping toward us through the dark, and this very sentence could be one of the last that ever gets to be true. That is the peculiar weight of this particular threat. With most of the dangers in this story, you can at least imagine surviving them, hiding, adapting, escaping somewhere else. With vacuum decay, there is no somewhere else. The failure is in the ground of reality, the same everywhere at once. So it takes the shelter and the refugee and the escape route all together. There is no high ground when it is the floor itself that gives way. It also does something quietly humbling to how you see the world. We walk around treating the laws of physics as eternal and absolute, the one thing we can truly rely on. Vacuum decay whispers that even they might be provisional, a local arrangement, a temporary setting that happens to allow us, and that could in principle be revised without warning and without appeal. The bedrock might be a thin crust over something deeper and stranger and utterly indifferent. Every other ending we have talked about leaves the universe still standing. The Earth burns, but the stars remain. The stars die, but space remains. The galaxies scatter, but the stage is still there. Vacuum decay is the only threat that erases the stage itself, that reaches past the actors and the scenery and unmakes the theater entirely. It is in the strictest sense the most complete ending imaginable, and it might be written into the fine print of the vacuum right now. But vacuum decay, for all its terror, is still a maybe. A dark possibility hanging on numbers we are not yet sure of, on a knife's edge we cannot quite read. There is, however, another flaw woven into the fabric of the universe that is not a maybe at all. We have measured it. We know it is there. It makes up most of the cosmos, and it is not waiting on some rare quantum accident. It is already, right now, pulling the entire universe apart. For most of the 20th century, cosmologists thought they understood the basic plot of the universe. It had begun in a Big Bang and had been expanding ever since, all the galaxies flying apart. The only real question was how the story would end, and nearly everyone assumed the answer came down to gravity, patiently pulling everything back, slowing the expansion year after year, like a ball thrown into the air losing speed as it climbs. It was a perfectly reasonable assumption. Gravity is attractive. Every galaxy pulls on every other galaxy. So the expansion ought to be gradually breaking, and the great debate was simply whether there was enough matter to eventually halt it and pull everything back together, or whether it would coast outward forever, slowing but never quite stopping. To settle the question, astronomers needed to measure how much the expansion had been slowing over cosmic history. So they went hunting for a cosmic ruler. They found one in a very particular kind of exploding star. When a certain type of dead star reaches a precise tipping point and detonates, it always blows up with very nearly the same true brightness, every single time. Astronomers call these type 1 a supernovae, and because they are so consistent, you can use how bright one appears from Earth to work out exactly how far away it is. Reliable cosmic mile markers, scattered across billions of years of the universe's past. In the late 1990s, two rival teams raced to measure the expansion using these exploding stars, each expecting to pin down exactly how much the universe was slowing down. In 1998, they got their answer, and it was not the one anybody had ordered. The distant supernovae were fainter than they should have been. They were further away than a slowing universe could possibly explain. The expansion was not breaking at all. It was speeding up. Let me make sure that lands properly. For billions of years, the universe has been expanding faster and faster, the galaxies flying apart at an ever-increasing rate, as though something were leaning on the accelerator. It was the exact opposite of what gravity should do. It was so strange and so thoroughly double-checked that the discovery earned the Nobel Prize, and it forced cosmology to admit an embarrassing fact. Most of the universe is made of something nobody can identify. We gave that something a name, and the name is really just a polite confession of ignorance. We call it dark energy. It is whatever is driving the expansion of the universe to accelerate, a kind of pressure woven into empty space itself, pushing outward, overwhelming the combined gravity of all the matter in the cosmos. We can measure its effects with real precision. What it actually is, we have almost no idea at all. And it is not some minor ingredient we can tuck away in a footnote. When you add up all the energy in the universe, dark energy makes up around 68% of the total. Dark matter, another mysterious thing we cannot see, makes up most of the rest. And all the ordinary matter, everything we can see and touch, every star and planet and person, every atom that has ever been studied, comes to about 5% of the whole. Sit with that ratio for a second, because it is genuinely humbling. Everything in every telescope image, every galaxy, every glowing nebula, all the visible glory of the cosmos, is a 5% trace floating on top of a universe overwhelmingly made of two things we cannot identify. We are a thin film of the familiar, drifting on an ocean of the unknown. And the larger, stranger part of that ocean, the dark energy, is the part that will decide how everything ends. The simplest explanation for dark energy is an old idea of Einstein's that he came to regret. When he first wrote down his equations for gravity, they insisted the universe had to be expanding or contracting, which he did not believe at the time. So he added a term to hold it still, a cosmological constant, a kind of energy belonging to space itself. When the expansion was discovered, he threw the term out, reportedly calling it his greatest blunder. It now looks as though he was right entirely by accident. Because a cosmological constant behaves exactly like dark energy. It is an energy inherent in empty space, so that every cubic meter of vacuum carries a tiny outward push. And this is the strange part. As the universe expands and makes more space, it makes more of this energy right along with it. So the push does not weaken as things spread out. It stays constant or even grows in total, which is precisely why the expansion can keep accelerating instead of fading away. There is a serious problem lurking underneath all this, though. When physicists try to calculate how much energy empty space should hold, using our best theory of the quantum world, the number they get is catastrophically wrong. It is larger than the amount we actually measure by factor, so enormous you would have to write it as a 1 followed by roughly 120 zeros. It is the single worst prediction in the history of physics, and nobody knows why the real value is so tiny. We are steering our fate by a quantity we fundamentally do not understand. Whatever dark energy turns out to be, its effect on the future is profound. As space expands ever faster, the distant galaxies are carried away from us more and more quickly. And beyond a certain distance, they end up receding faster than their own light can cross the growing gap between us. When that happens, their light can never reach us again. They cross a kind of horizon, a cosmic point of no return, and slip forever out of view. Run that forward far enough, and the sky empties out. One by one, over billions of years, every galaxy outside our own local family will race across that horizon and vanish from the observable universe. The light they sent out long ago will keep arriving for a while, stretched and dimmed and reddened, until it fades below anything we could ever detect. Eventually, the entire rest of the universe simply disappears from our reach, pulled away into the dark faster than light can bridge the distance. There's a genuinely eerie consequence to this. Imagine astronomers living in that far future, on some world in our merged galaxy, 100 billion years from now. They would look out and see only their own island of stars, ringed by perfect total blackness. No other galaxies, no sign of the expansion, no trace of the Big Bang left anywhere to find. The truth about the universe, the very facts we have worked so hard to uncover, will have been erased by the expansion itself. They would have no way to know any of it. That thought stops me every time. We may be living in a rare, brief window when the universe is still young enough to read its own history, when the evidence of how everything began is still visible in the sky. Later observers, through no fault of their own, will be born into a cosmos that lies to them by omission, that shows them a small, lonely island and hides the vast, receding rest. Some knowledge, it turns out, has an expiration date, written into the expansion of space itself. And dark energy does far more than empty the sky. It holds the deciding vote on how the universe itself will end. If it stays exactly constant, the cosmos keeps expanding and cooling forever, drifting toward a slow, cold, quiet death. If it were somehow to weaken and reverse, gravity could win in the end and drag everything back together. And if it grows stronger with time, it leads to the most violent finale of all, a tearing apart of everything that exists. Which of those it will be depends on the precise nature of dark energy, on a single number that describes how its push changes as the universe expands. And we do not yet know that number well enough to be sure. We are, in effect, still waiting to find out which kind of ending the largest and least understood part of the universe has quietly chosen for us. It is worth admitting how shaky our footing really is here. Different ways of measuring the expansion of the universe keep giving slightly different answers. A genuine disagreement that has come to be called the Hubble tension, and it stubbornly refuses to go away. Some very recent surveys have even hinted that dark energy might not be perfectly constant after all, that it may be slowly changing over cosmic time. If that holds up, it would rewrite our picture of the future all over again. We are still, quite clearly, missing something large. That is the quietly terrifying thing about dark energy. It is not a distant object we might dodge, or a rare event we might outlast. It is the dominant feature of the entire universe, present in every scrap of empty space, and it is actively shaping the fate of everything, right now, by rules we have barely begun to read. The majority of reality is a force we cannot even name, and it is not on our side. For now, if dark energy simply holds steady, the ending it points toward is a slow one. A long, gradual drift into cold and dark and isolation, over spans of time we can barely name. But there is that other possibility, the one where dark energy does not hold steady, where instead it grows and strengthens and turns genuinely vicious. In that version, the end is neither slow nor gentle. It is a violent unraveling of everything, right down to the atoms in your own body. They call it the Big Rip. Picture the last half hour of the Earth. Not an asteroid this time, not a swollen dying sun, nothing striking us at all. Instead, the sky is emptying. The other planets have already drifted away and vanished. The sun is receding, its grip on us failing. And the Earth beneath your feet is beginning, very slightly, to come apart, the ground straining upward, the air thinning, as space itself pulls the whole planet gently, then not so gently, into pieces. This is what the Big Rip would look like from inside. This ending only happens if dark energy is a particular and especially nasty kind of thing. Everything we said in the last chapter assumed dark energy stays more or less constant. But what if it does not? What if, instead of holding steady, dark energy slowly strengthens as time goes on, its outward push growing and growing without any limit? Physicists have a name for that darker version. They call it phantom energy. The scenario was laid out in 2003 by a team of physicists led by Robert Caldwell, and they gave it a suitably brutal name, the Big Rip. The idea is simple to state and horrifying to follow through. If dark energy keeps getting stronger, then the acceleration of the universe does not merely continue. It runs away faster and faster until the expansion becomes infinite in a finite amount of time. There would be an actual date on which the universe tears itself to shreds. To see why that is so different, you have to understand something about the expansion of space. Normally, it only matters on the very largest scales in the gaps between distant galaxies. It does not stretch you, or the Earth, or even our galaxy, because gravity and the other forces holding those things together are far too strong for the gentle push of ordinary dark energy to overcome. The bound things stay bound. Only the empty spaces between islands of matter grow. The Big Rip changes that catastrophically. As phantom energy strengthens, its push grows strong enough to overpower gravity at smaller and smaller scales, working its way steadily inward. First, it beats the weak pull holding distant galaxies together. Then a stronger pull holding a single galaxy together. Then the grip of a star on its planets. Then a planet's hold on itself. And then, at the very end, the forces binding molecules and atoms and the particles inside them. It unbinds the universe from the outside in. And because phantom energy grows without limit, this all builds toward a fixed and final moment. A deadline. In one version of the mathematics, that moment lies something like 20 billion years or so in the future, though the exact date depends on the precise nature of dark energy. Whenever it falls, the last few million years, and then the last few minutes before it would unfold in a very particular and terrible order. It would begin quietly on the largest scale. Roughly 1 billion years before the end, the great clusters of galaxies, held together only loosely by gravity, would be pried apart, their members scattered into isolation. The cosmic web, the vast structure that organizes all the galaxies, would come undone, dissolving into lonely islands drifting ever further from one another. At this stage, nothing local would seem wrong at all. The catastrophe would still be safely far away, out among the galaxies. It would reach our own galaxy. Perhaps 60 million years before the end, the expansion would grow strong enough to overwhelm the gravity binding a galaxy together. Andromeda, or whatever our merged home has become by then, would begin to disperse, its stars drifting apart, the great disk coming loose and spreading out into the dark. The galaxy would evaporate quietly, star by star, dissolving like a sugar cube in water. Closer to the end, it would come for individual solar systems. A few months before the final moment, the expansion would pry planets loose from their stars. Any world still orbiting any sun would feel the grip loosen and then fail, and drift away into the widening dark. The tidy little clockwork systems that had somehow survived everything else, the last quiet refuges of order, would come undone in a matter of weeks. And then it would come for a world like the Earth. In the final half hour, the expansion, now unimaginably strong, would overpower the gravity holding a planet together. The planet's own weight, which had bound it into a sphere for billions of years, would no longer be enough. The ground would begin to rise. The oceans and the air would lift away. The whole planet would swell and crack, and finally burst apart into fragments flung into the growing void. The last moments are almost beyond imagining. In the final fraction of a second, the expansion would reach far past planets and stars and tear apart matter itself. Molecules would be pulled apart into atoms. Atoms would be ripped into their nuclei and electrons. And then the nuclei, the incredibly tightly bound hearts of atoms, would be torn open too. Everything that had ever been assembled, at every scale, would be disassembled all the way down in a single instant. And at the very end, some versions of the theory suggest the expansion would tear apart the fabric of space-time itself, reaching a true and absolute limit, a point beyond which the equations simply stop making sense. Not a slow fade, not a cooling into the dark. Instead, a hard and final rupture of everything, everywhere in the same instant. The universe would not wind down. It would be ripped open, and then there would be nothing left to rip. What makes the Big Rip so uniquely unsettling, to me, is that it comes with a clock. Most cosmic endings are slow beyond comprehension, fading out over spans of time, so vast the distinction between happening and not happening almost dissolves. The Rip is different. It has a deadline, a specific moment, racing toward every particle in existence at once. It takes the quiet, patient stretching of space, the gentlest thing in all of physics, and turns it into the most violent death imaginable. There is real comfort to be had here, thankfully. The Big Rip is only one possible future, and at the moment it is not the frontrunner. Our best measurements of dark energy are still broadly consistent with it staying constant. The milder case, which leads to a slow cold ending rather than a violent tearing. For the Big Rip to happen, dark energy has to be that special phantom kind that strengthens over time, and the data does not currently demand it. But it does not rule it out either, and that is the catch. We simply do not know the nature of dark energy well enough to close the door. As we saw, some recent surveys have hinted that dark energy might be changing over cosmic time, and if it is changing in the wrong direction, the rip comes right back into play. The honest answer is that the most violent possible end of the universe remains on the table, waiting on a number we have not yet managed to pin down. Whether the ending is a rip or a slow freeze, though, dark energy has already sealed one part of our fate. The isolation is coming no matter what. The galaxies are receding, the sky is slowly emptying, and the universe is drifting toward loneliness and cold. So let us set the Big Rip aside as the rarer and more dramatic possibility, and follow the likelier path instead. The gentle one, the slow one, because in its own quiet way, it is every bit as final, and perhaps even sadder. The slow ending does not announce itself. There is no deadline, no dramatic rupture, no single terrible moment. It simply creeps in over spans of time that make everything we have discussed so far look sudden. And it begins in the most poignant way imaginable with the very thing that has defined the universe for its entire history so far. It begins with the stars going out. Look up at the night sky, and it is easy to believe the stars are eternal. They have shone over every human who ever lived, every civilization, every story ever told. They feel like the permanent backdrop against which everything else happens. But the stars are not the backdrop. They are a phase, a chapter, and it is a chapter that, on the timescale of the universe, is going to end surprisingly soon and then never begin again. So follow me forward, past the death of the sun, past the merger of the galaxies, past every event we have talked about, into the genuinely deep future of the cosmos. Trillions of years from now, so far ahead that the entire history of the universe up to this moment will seem like a bright, brief flash at the very beginning. Out there, in that unthinkable distance of time, the age of starlight comes quietly to an end. There will be a last star, a final point of light, burning somewhere in a dark and emptying cosmos, the last fire of its kind anywhere in existence. And one day it too will flicker and cool and go out. And when it does, the longest night imaginable will begin, a darkness with no morning waiting at the end of it. To understand how the universe truly dies, we have to be there for that final light. So let us go and watch it fail. Somewhere in the unimaginably distant future, on some cold world or on no world at all, there will be a final night. A last star, the very last one burning anywhere in the entire universe, will grow dim and flicker and fade to nothing. And for the first time since almost the beginning, the cosmos will contain no starlight at all. Not dimmed, not distant, simply gone. That final darkness is where all of this has been heading, and it is closer to inevitable than anything else in this story. To get there, we have to leave behind every timescale we are used to. Human history is a few thousand years. The age of the universe, so far, is under 14 billion. The future we are stepping into now runs to trillions of years and far, far beyond, so vast that the entire past of the cosmos, everything from the Big Bang until this very moment, will come to seem like the first faint second of an extraordinarily long life. We happen to live in what astronomers call the stelliferous era, the age of stars. It is the chapter of cosmic history when the universe is full of light, when galaxies blaze and new suns are constantly being born. To us, it feels like simply the way things are, the natural state of reality. But it is a passing phase, a season, and like every season, it has both a beginning and an end. We are living in the bright part. It will not last. Everything depends on gas. Stars are born when great clouds of hydrogen gas collapse under their own gravity and ignite. That gas is the raw fuel of the cosmos, the stuff from which every star is made. And here lies the simple, fatal problem. There is only so much of it, and once it is used up, it does not come back. Every star that has ever formed has drawn down a finite supply that can never be truly refilled. We are already well past the peak. The universe hit its great baby boom of star formation billions of years ago, at a time astronomers sometimes call cosmic noon, when suns were being born far faster than they are today. Since then, the rate has been steadily falling. Right now, across the whole universe, the fires of star birth are slowly dying down. We are, without quite realizing it, living in the long afternoon of the age of stars. The reason is that gas keeps getting locked away. When a star dies, some of its material is thrown back into space to make new stars, but a great deal of it is trapped forever, sealed inside dead remnants that will never burn again. White dwarfs, neutron stars, black holes. With every generation of stars, a little more of the universe's fuel is taken out of circulation for good. The tank is draining, and there is no way to fill it back up. Eventually, the gas runs too thin to make new stars at all. Estimates vary, but somewhere in the neighborhood of 100 trillion years from now, the last star will form, condensing out of the last usable wisp of gas in the entire cosmos. After that, no new suns ever. The universe will hold only the stars that already exist, and every one of them will be burning down toward its own inevitable death, with no replacements coming behind them. And the stars die in a strict order dictated by their size. The largest and brightest go first, as we saw with the supergiants. They burn ferociously and die young, in mere millions of years, in supernovae. So in the deep future, one by one, the brilliant blue giants wink out, and no new ones are ever born to take their place. The most spectacular lights in the sky are the first to be lost. Next go the stars like our sun, modest, steady, yellow stars that burn for roughly 10 billion years before swelling into red giants and collapsing into white dwarfs. Exactly the fate that awaits our own star. Over tens of billions of years, they too fade from the cosmos, shedding their outer layers, leaving behind only slowly cooling embers. The familiar kind of star, the kind that warms worlds like ours, gradually disappears from the universe altogether. What is left at the very end are the runts, the smallest, dimmest, coolest stars of all, the red dwarfs. They are far less impressive than the sun, giving off only a fraction of its light, glowing a deep and feeble red. For most of cosmic history, nobody would give them a second glance. But in the long death of the universe, these unremarkable little stars turn out to be the last ones standing, and by an enormous margin. The secret of the red dwarfs is that they are misers. They are so small and burn so slowly and stir their fuel so thoroughly that they can keep going for an almost absurd length of time. Where the sun lasts 10 billion years, the smallest red dwarfs can burn steadily for 10 trillion years, and perhaps far longer still. They are the marathon runners of the cosmos, the patient survivors, hoarding their little fires long after every grander star has died. So picture the sky across these enormous spans of time. The blue giants, long gone. The yellow suns, gone. The universe grows dimmer and redder and emptier, age after age, until at last it is lit only by the faint red glow of dwarf stars scattered thinly through the dark. A cosmos of embers. Still, technically, an age of stars, but a dim and failing one, guttering toward its close. And even the red dwarfs cannot last forever. One by one, across trillions of years, they exhaust the last of their fuel and begin to fade. There is no drama in it, no supernova, no grand finale. A red dwarf simply cools and dims and quietly shrinks into a dying ember, its long, patient fire at last spent. The final generation of stars burns down like the last coals of fire that nobody is left to tend. Which brings us, at last, to the final star. Somewhere, in some far corner of the dark and thinning universe, there will be one red dwarf that outlasts every other, the last star still burning anywhere in existence. For a while it will glow on, alone, a single point of warmth in an ocean of black that stretches beyond all sight, the very last fusion happening anywhere in the cosmos. And then its fuel will run out too. When that final star fades, something changes that has never changed before, not once in the entire history of the universe. For over 100 trillion years, ever since the first stars ignited a few 100 million years after the Big Bang, there has always been starlight somewhere. Always a fire burning, always a source of warmth and light. With the death of that last red dwarf, for the first time ever, there is none. The universe goes dark completely, and it will never light up in that way again. Try to feel the weight of that moment, even though no one will be there to feel it. Every sunrise that has ever happened, every star anyone ever wished on, every warm afternoon, every dawn over every world in the whole history of the cosmos, all of it belongs to a single bright chapter, now closed. After this, there are no more sunrises anywhere forever. The age of starlight is over, and the age of the long dark has begun. What remains is a graveyard. The universe of the far future is a vast, cold, dark expanse littered with the corpses of stars. White dwarfs, slowly cooling toward black. Neutron stars, spinning down. Dead planets, frozen solid. Brown dwarfs that never quite managed to shine. All of it drifting through a darkness so complete that our own night would seem, by comparison, blindingly bright. This is called the degenerate era, and it lasts a very, very long time. Every so often, in that long darkness, there might be a brief flicker. 2 dead stars, 2 white dwarfs perhaps, drifting for eons, could by sheer chance collide, and for a single moment blaze into a supernova, one flash of light in the black. Or 2 brown dwarfs might merge and briefly kindle a small new star. But these are accidents, rare and fleeting sparks in an overwhelming dark. They are not a new dawn. They are just the embers settling. It is worth sitting with what this means for us, for the age we actually live in. We tend to think of ourselves as arriving late, billions of years after the beginning, on a middle-aged planet around a middle-aged star. But by the true measure of the universe's lifespan, we are astonishingly early. We exist in the brief, brilliant morning of the cosmos, in the tiny sliver of time when the stars still shine. Almost the entire future of the universe is darkness, and we will have missed all of it. That is a strange kind of privilege when you turn it over in your hand. Of all the eras the universe will ever pass through, the overwhelming majority of them cold and dark and dead, we happen to open our eyes during the one age when the lights were still on. We were born into the season of stars. It is easy to take that for granted, to assume starlight is simply a permanent feature of reality. It is not. It is a fleeting condition, and we are living right inside it. But the death of the stars is not quite the end of the story, nor even the end of structure in the universe. Because in the long dark that follows, something still rules. The corpses of the smaller stars simply drift and cool. But the largest, densest, most dangerous objects the universe ever made do not fade away so easily. They remain, growing, waiting, patient. In the endless night that is coming, the universe will belong to the black holes. There is a chapter of the universe's life so long that it makes every age we have discussed so far, the age of stars, the age of dead remnants, all of it look like a brief flash at the very start. It unfolds in complete darkness, over spans of time with no real comparison in human language. And through the whole of it, the universe is ruled by a single kind of object. The black holes have inherited the cosmos, and they will hold it for very nearly an eternity. remember where we left things. The last star has died. The universe has become a vast, dark graveyard, scattered with the cooling corpses of stars, white dwarfs and neutron stars, dead planets, failed suns, all drifting through a blackness beyond anything we can picture. It seems like a final state. It is not, because even those corpses, it turns out, are not permanent. Even matter itself may have an expiration date stamped into it. This is one of the strangest ideas in physics, and we are not yet certain it is true. Our best theories hint that the proton, one of the basic building blocks of every atom, of everything you have ever touched, may not be perfectly stable. Given enough time, a proton may simply fall apart, decaying into lighter particles and radiation. And if protons decay, then everything made of them is living on borrowed time, no matter how solid and permanent it looks. The catch is the timescale, which is almost funny in its enormity. If protons do decay, a typical one would last something like a 1 followed by 34 zeros in years, or even longer. That is a stretch of time so far beyond the current age of the universe that the comparison is meaningless. But in the deep future we are now exploring, there is nothing left but time. And given enough of it, even the most impossibly patient decay runs all the way to completion. So across a span of maybe 10 to the power of 40 years, the dead remnants slowly dissolve. Proton by proton, the white dwarfs evaporate. The neutron stars come apart. The dead planets, the cold rocks, the frozen wisps of the last atmospheres, all of it very gradually turns to radiation and drifts away. The graveyard itself decays. The tombstones crumble to dust, and then the dust crumbles to nothing at all. There is something almost tender about the very end of ordinary matter. As the last remnants slowly evaporate through proton decay, they give off the faintest possible warmth, a final trickle of energy. For an unimaginable stretch, the dying white dwarfs are the last dim sources of any heat at all in the universe, glowing so feebly you would have to press against one to notice. The last warmth in all of creation, fading proton by proton into the dark. And when that is done, when the last atom of ordinary matter has decayed away, only one kind of thing is left standing. The black holes. They alone survive the death of matter, because they are not made of atoms in any normal sense. They are pure gravity, regions where space-time itself has folded shut, and proton decay has no hold on them. The universe enters its longest age of all. Astronomers call it simply the black hole era. Try to picture it, though there is almost nothing to picture. An utterly dark, near-empty universe, expanding, cold beyond meaning, holding here and there a scattering of black holes, each one impossibly far from the next. No stars, no planets, no light, no matter as we would know it. Just these silent wells of gravity, drifting alone in an ocean of blackness, the last islands of structure in a dissolving cosmos. And they come in a great range of sizes. The smaller ones, left behind by individual dead stars, a few times the mass of the sun. And the giants, the supermassive black holes from the hearts of the old galaxies, grown over the eons by swallowing everything they could reach, now holding millions or billions of times the mass of the sun. The merged monster at the center of our own dead galaxy would be among them, vast and patient in the dark. For a long time, physicists thought black holes were truly forever. Once formed, nothing escapes them, so it seemed they could only ever grow, or at most sit unchanged for all of eternity. And then, in 1974, a young Stephen Hawking worked out something that stunned everyone. Black holes are not entirely black. They very slowly leak, and anything that leaks, given enough time, eventually runs dry. The effect is called Hawking radiation, and it arises from the strange behavior of empty space right at the edge of a black hole. Through a quirk of quantum physics, the black hole slowly radiates away a faint trickle of particles, and in doing so it loses a tiny sliver of its mass. Bit by bit, Unimaginably slowly, it shrinks. The most inescapable object in the universe is, it turns out, quietly evaporating like a puddle drying in the sun, only across spans of time that defy all reason. And here is the beautiful backwards part. The bigger the black hole, the slower it evaporates. The giants take the longest of all to die. A black hole with the mass of the sun would take something like 10 to the power of 67 years to fully evaporate. The supermassive ones, the true titans, need far longer, up to around 10 to the power of 100 years. That last number has a name. It is called a googol, a 1 with 100 zeros trailing behind it. It is genuinely impossible to feel a number that large, so let me try to frame it. The universe right now is about 14 billion years old. Set against a googol of years, the entire history of the cosmos so far, everything from the Big Bang through the stars and the galaxies and us, does not merely look small. It rounds to zero. It is a rounding error at the very first instant of a story, almost unthinkably longer than everything that has happened up to now. For nearly all of that vast lifetime, a black hole barely changes. Its evaporation is so slow as to be effectively invisible, a whisper of particles trickling out into the dark, century after century, eon after eon, while the hole sits almost exactly as it was. If you could somehow watch one, you would see nothing happen for spans of time, next to which the age of the universe is a single blink. Patience, on a scale only the cosmos itself can manage. But at the very end of its life, a black hole finally quickens. As it shrinks, it radiates faster and grows hotter and shrinks faster still, the whole slow process suddenly running away in its final moments. And then, after almost an eternity of near stillness, the black hole vanishes in a last flash of energy, a small bright burst in the dark, the final flourish of an object that took a googol years to die. And then it is simply gone. One by one, across spans of time that make the mind go blank, the black holes evaporate and disappear. The small ones first, then the larger, then at last the greatest of them all. And somewhere out there, around 10 to the power of 100 years from now, the final black hole, the biggest and most patient in the whole universe, will radiate the last of its mass and wink out in a faint final flash. The last structured object in all of existence gone. Think about what that flash actually is. It is the last event. For the entire history of the universe, there's always been something happening somewhere. A star burning, a world forming, a black hole feeding, a proton decaying. The evaporation of that final black hole is the last discrete thing that ever occurs, the last flicker of activity in a cosmos winding all the way down to absolute stillness. After it, the universe has nothing dramatic left to do, ever again. What remains afterward is almost nothing at all. A universe stretched vast and thin and utterly dark, containing only a dwindling fog of stray particles, lone electrons, faint photons, ghostly neutrinos, drifting endlessly further apart in the expanding void. No stars, no matter, no black holes, no structure of any kind. Just a thinning mist of the last leftovers, cooling toward a temperature it will approach forever and never quite reach. There's a profound loneliness to this era that I find hard to shake. Even in the darkest chapters before it, the universe still had characters. Dead stars, silent black holes, something, at least, to break the emptiness. Now, even those are gone, evaporated into a haze so sparse that a single particle might drift for eternities without ever meeting another. The universe becomes dark, and then something worse than dark. It becomes empty in the deepest possible sense, alone with itself, and barely even that. And this is the destination for the black holes and for everything else. Every grand structure the universe ever built, every galaxy, every star, every monster of gravity has been a temporary arrangement, a knot of order that the cosmos would eventually undo. The black holes were simply the most stubborn knots of all, the last to be untied. Even the kings of the endless night are mortal. Even the monsters, in the end, evaporate. But the evaporation of the last black hole, strange as it sounds, is still not the true end. It is the last event, yes, and an event is a thing that happens, so after it there is one final state left for the universe to settle into. Not another catastrophe, not another age, a condition, the deepest, quietest, most complete ending of all, in which the very idea of anything happening becomes impossible. We have arrived at the doorway of heat death. For 18 chapters, we have watched the universe kill in every way it knows how. With fire, with ice, with radiation, and gravity, and the tearing of space, and the slow starvation of the light. But the true end of everything, the final state the cosmos settles into and never leaves, is none of those things. It is not violent at all. It is stillness. Perfect, total, eternal stillness. And it is the most frightening thing in this entire story. We have followed the universe all the way down. The world's burned. The stars went out. The galaxies scattered, and the black holes evaporated. What is left is a thin, cold, dark haze of particles, drifting apart in an expanding void. And now, that universe faces its last and permanent condition, the one it has been sliding towards since the very first instant of the Big Bang. Physicists call it the heat death. To understand it, we need one idea, perhaps the deepest idea in all of physics. That idea is entropy. It sounds technical, but at its heart, it is simple. And once you see it, you start to see it everywhere. Entropy is a measure of how spread out, how mixed, how even out things are. Low entropy means order and difference, energy concentrated in one place, a hot thing sitting next to a cold thing. High entropy means sameness, everything smooth together, all the difference is gone. And there's an iron law that governs which way it goes. That law is the second law of thermodynamics, and it is about as close to unbreakable as anything we know. It says that in the universe as a whole, entropy always increases. Things always, on balance, move from order toward disorder, from difference toward sameness. Never the other way around, not once, not ever on a large scale. The universe is a one-way street, and it runs downhill toward evenness, always and everywhere. You watch this happen every single day without ever thinking about it. Drop ink into water, and it spreads out and mixes, and it never gathers itself back into a neat drop. Pour hot coffee, and it cools to room temperature, sharing its heat with the air, and it never spontaneously reheats. A sandcastle crumbles into a flat beach. Order falls apart into disorder on its own, everywhere, all the time. That is entropy quietly running the world. Now here is why any of this matters for the fate of the universe. To make anything happen, anything at all, you need a difference. A gradient, hot flowing to cold, high falling to low, energy moving from where there's a lot to where there is little. That flow is what drives every process there is. A star shines because its blazing core is so different from cold space. You are alive because your body can exploit the difference between the food you eat and the waste you give off. Difference is the engine of everything. And every single time that engine runs, it spins some of the difference down. Every star that shines, every fire that burns, every thought you have ever had takes a little of the universe's order and cashes it in, nudging the whole cosmos one step closer to sameness. All of existence, every event since the beginning of time, has been living off the supply of order that the Big Bang provided. And that supply, though staggeringly large, is not infinite. So follow it to its conclusion. Every star burning, every black hole evaporating, every particle interacting, all of it is spending the universe's dwindling store of difference. Bit by bit, the hot places cool and the cold places warm, the concentrations spread out, the gradients flatten, and eventually, inevitably, the universe runs all the way down. It reaches a state where everything is the same temperature, the same in every direction, with no differences left anywhere at all. Maximum entropy. That state is the heat death, and its horror is not obvious at first. The universe is not destroyed. The energy is not gone. In fact, not a single scrap of energy has been lost, because energy is always conserved. It is all still there. It has just been spread out so perfectly, so evenly, smeared so uniformly across all of space, that not one bit of it can ever again be used to make anything happen. Because with no differences left, there is no flow. And with no flow, there is nothing to drive any process, anywhere, ever. No star can shine, because there is no cold left to pour its heat into. No chemistry can happen. No structure can form. No machine can turn. No signal can travel. No thought can think. Every possible event requires a difference to run on. In the heat death, all differences are gone. Forever. This is what makes it the deepest ending of them all. It is the end of life, of course, but it is far more total than that. It is the end of anything ever happening again, anywhere in the universe for the rest of eternity. Not a pause. Not a long, dark age with a dawn somewhere far ahead. A permanent, changeless, universal stillness, out of which nothing can ever emerge, because the very thing that makes emergence possible has been used up. And the temperature keeps falling forever. As the universe goes on expanding, that last uniform haze of particles is stretched thinner and thinner. It grows colder and colder, sliding down toward absolute zero, the coldest temperature there can possibly be. It never quite arrives, but it approaches without end, an eternal, deepening chill in an eternal, deepening dark. Cold beyond any cold that has ever existed, and getting colder always. Perhaps the strangest casualty of a heat death is time itself. We feel time flowing in one direction, from past to future, and the reason we feel that, physicists believe, is entropy. The past is the direction of more order, the future the direction of more disorder. That steady increase is the arrow of time, the very thing that makes tomorrow different from yesterday. But at maximum entropy, there is no more increase because there is nothing left to increase. And when entropy stops changing, the arrow of time loses its point. There is no difference between one moment and the next, because nothing distinguishes them. Nothing happens to mark the passage from one to the other. Before and after become meaningless words. In a very real sense, at the heat death, time itself quietly stops mattering. There is no cosmic clock that halts. There is simply no longer any way to tell that a clock was ever ticking. It is worth pausing on how different this is from the other endings we have seen. The Big Rip is fast and furious, over in an instant of violence. A gamma ray burst is sudden, a supernova spectacular, an asteroid a single terrible day. The heat death is the exact opposite of all of them. It is not an event. It is the absence of all further events, stretched out across an entire eternity. It does not strike. It simply, permanently settles. And this, according to our best current understanding, is the most likely way the universe actually ends. Set aside the maybes, the vacuum decay we're not sure of, the big rip that needs a special kind of dark energy. If dark energy is what it most appears to be, steady and constant, then this quiet, cold, uneventful stillness is where everything is headed. Not a maybe, the default, the path of least resistance for the whole of reality. There is a bleak irony hiding in the name. We call it the heat death, and yet it is the coldest state imaginable, a universe hovering just above absolute zero. The name comes from the older meaning of heat, the flowing of energy from hot to cold that does all the work in the cosmos. The heat death is the death of that flowing. The moment the flow stops forever. It is not death by heat. It is the death of heat itself, as a force that can ever do anything. Sit for a moment with what is actually lost, not in a burst, not in a scream, just a slow and total fade. Every song ever sung, every equation ever solved, every sunrise, every war, every kiss, every discovery, Every last thing that any mind anywhere ever cared about, all of it dissolved into a uniform, lukewarm, featureless haze spread evenly across an endless dark. Not remembered, not mourned, simply smoothed away until there is no one and nothing left to have ever known it happened. The universe is not destroyed in the end. It is worse than destroyed. It persists forever, entirely unable to do a single thing. It becomes an eternity of existence without a single event, being without becoming a something that can no longer manage to be anything in particular. If there were a word darker than nothing, this would deserve it. The lights do not merely go out. The very possibility of light, of change, of anything at all, goes out along with them. And it stays that way. That is the part one keep returning to. There is no rescue waiting in the far distance, no cycle bringing it back around, no dawn at the end of this particular night, at least not in the simplest version of the story. The heat death is not a low point the universe passes through on its way to somewhere else. It is the destination, the final and permanent state, and once reached, it lasts for an eternity that makes the entire prior life of the cosmos look like a single fading spark. So there it is, the true end of everything, as our best physics currently paints it. Not fire, not a monster, not a tearing, just an endless, uniform, freezing calm in which nothing happens and nothing can happen, and time itself has forgotten how to move. Every threat in this film, every asteroid and flare and wandering black hole was only ever hurrying us, in the end, toward this. The quietest apocalypse of all, the one that does not roar. It simply patiently closes, and that should be the end of the story. A cold, still, eternal nothing with no way out. Except that every single word of it rests on one enormous assumption, that the universe gets only one life. One beginning, one arrow of time, one long slide into the dark, and then nothing forever. But what if that assumption is wrong? What if this ending, as final as it looks, is not truly the end? What if it is something stranger? A pause, a turning, the space between two heartbeats. Take a breath, because we're going to climb back out of the dark for a while. Everything we have just described, the last star, the last black hole, the endless frozen stillness, all of it assumes the universe gets a single life, and then nothing. One long exhale into the cold. But there are physicists, serious ones, who suspect the universe might not work that way at all, who wonder whether the final dark is less like a death, and more like the pause between one breath and the next. The oldest version of this hope is called the Big Crunch, and it is the exact mirror image of the Big Bang. We know the universe is expanding, but imagine that one day the expansion slows, stops, and reverses. Imagine gravity finally winning and beginning to pull everything back together. All the galaxies that spent billions of years flying apart would begin, slowly at first, to fall back and toward one another. Run that collapse forward, and it becomes terrifying in its own right. The galaxies rush together. The sky, instead of emptying, fills and brightens. The background of space itself heats up from cold to warm to searing. The stars are swallowed into a growing inferno as the whole universe contracts toward a single, unimaginably hot and dense point, a Big Bang running in reverse. Everything that ever existed crushed back into the fire it first came from. For the Big Crunch to happen, dark energy would have to betray its current behavior, to weaken and stop pushing and let gravity take back over. And honestly, our best measurements do not favor that. Dark energy looks, for now, like it will keep pushing forever, driving the cold ending instead. But we understand dark energy so poorly that we cannot rule the reversal out. The universe could yet fall back in on itself. We simply do not know for sure. Still, notice what the Big Crunch offers that the heat death cannot. An ending with the possibility of a sequel. Because if the universe can collapse back into a hot, dense point, then perhaps, just perhaps, it does not have to stop there. Perhaps it does what it did once before. Perhaps it bounces. This is the idea of the Big Bounce, and it turns a final crushing catastrophe into a fresh beginning. In these models, the collapse does not end in a permanent full stop. Instead, at the moment of maximum compression, the universe rebounds, exploding outward again into a brand new Big Bang, a fresh cosmos rising from the ashes of the old. And if it can happen once, there is no obvious reason it cannot happen again and again without end. Some physicists have built entire cosmologies around this rhythm. In one family of models, championed by Paul Steinhardt and Neil Turok, the universe goes through endless cycles, each one billions of years long, expanding and cooling and then contracting and bouncing over and over forever. A cosmos that breathes. No single beginning, no final end, just an eternal succession of universes, each one born from the death of the last. It is a genuinely comforting picture, right up until you look closely at the cost. Because in every one of these cyclic models, each new universe is wiped clean of the one before it. The bounce or the crunch obliterates all the structure, all the memory, everything. So even if the cosmos is eternal, endlessly reborn, our universe, this one, with its particular stars and galaxies and its single brief flowering of life, still ends completely and never returns. Eternity for the cosmos, oblivion for us. There is a stranger idea still from one of the most brilliant and unconventional minds in physics, Roger Penrose. He calls it conformal cyclic cosmology, and it begins from the heat death itself, from that final, cold, empty universe we spent the last chapter dreading. Penrose looked at that ultimate state and noticed something very odd about it, something almost mystical hiding in the mathematics. In the deep heat death, all the matter is gone. All that remains is radiation, massless particles like photons, drifting through an endless void. And here is the strange thing. Without any mass, the universe loses its rulers and its clocks. There is nothing left to measure size or time against. And when you lose all sense of scale, Penrose argues, an unimaginably vast, cold, empty universe becomes mathematically indistinguishable from an unimaginably tiny, hot, dense one. The end starts to look exactly like a beginning. So in Penrose's vision, the heat death of one universe does not just resemble a Big Bang. It becomes one. The cold, empty, infinite far future of our cosmos is, in the deepest mathematical sense, the fiery birth of the next. He calls each of these universes an aeon, and he imagines an endless chain of them, each one's death seamlessly becoming the next one's dawn, stretching back forever and forward forever. It sounds like pure poetry, but Penrose insists it might leave fingerprints. He has claimed to find faint patterns in the cosmic microwave background, the leftover glow of our own Big Bang, that could be echoes bleeding through from a previous aeon, the scars of ancient events that happened before a universe began. Most cosmologists are deeply skeptical, and the evidence is fiercely disputed. But the very idea that we might glimpse a ghost of the universe before ours is extraordinary. So there is hope here of a kind. Bounces, cycles, eons, a cosmos that never truly dies but only turns over and begins again. But I have to be honest about the shadow that falls across all of it. Because once you allow that the universe might be eternal or infinitely repeating, you open the door to one of the most quietly horrifying ideas in all of science. And once it is in your head, it is very hard to get back out. It goes back to Ludwig Boltzmann, the physicist who first truly understood entropy. He realized that the second law is really about probability. Disorder is overwhelmingly more likely than order, which is why things fall apart. But overwhelmingly likely is not quite the same as certain. Given enough time, random chance can briefly, accidentally, assemble order out of chaos. And in an eternal universe, there is infinitely more than enough time. Think about what that means in a cosmos that lasts forever. In the endless heat death, particles drift at random, almost always staying in bland, featureless equilibrium. But every so often, by pure fluke, a handful of them will randomly clump into something ordered, usually something trivial. But given infinite time, the fluctuations will occasionally, astronomically rarely, produce something genuinely complex. And on a long enough timeline, they will produce, out of sheer randomness, a working, conscious brain. It has a name, a Boltzmann brain, a mind that flickers into existence out of the random noise of a dead universe, complete and fully formed for a single fleeting moment. It would have thoughts. It would have memories of a childhood, of a world, of a whole life, all of them completely false, assembled at random along with the rest of it. And then, almost instantly, the fluctuation would disperse, and the brain and its entire imagined life would vanish back into the noise. And here's the part that genuinely unsettles cosmologists. In a universe that lasts forever, there would be more of these random, momentary brains than there are real, evolved observers like us. Vastly, unimaginably more, which leads to a truly vertiginous question. How do you know that you are not one of them? How can you be certain you are a real person, with a real past, and not a brief fluctuation in an endless dark, dreaming a life that never happened, about to dissolve? Most physicists treat the Boltzmann brain less as a real prediction and more as an alarm bell. If a theory of the universe implies that most conscious observers are random flickers with false memories, then something is probably wrong with the theory, and out it goes. It is a tool for spotting bad models, but it is a deeply uncomfortable tool because escaping it cleanly, proving that we're the real observers and not the fluctuations, is far harder than it sounds. So this is where the hope leaves us. Every door that seemed to open onto rescue turns out to have something strange waiting behind it. The cyclic universe offers eternity, yet erases us completely with each turn. Penrose offers rebirth, on evidence almost nobody accepts. And the eternal cosmos, the one that lasts long enough to bounce forever, quietly suggests that our very sense of being real might be an illusion flickering in the dark. Hope, yes, but hope with a very long shadow. So let us set all of it aside. The crunches and the bounces, the eons and the fluctuations, the endings and the maybe beginnings. Set aside every speculation about what comes before or after or instead. And come back, finally, to the one thing in this entire story that we actually certainly know. The one fact that none of the darkness and none of the doubt can touch. Right now, against all of it, we are here. And that may be the most astonishing thing of all. Here, at the end of all of it, I want to tell you the single strangest fact in this entire film. Out of the whole life of the universe, from the fire of its birth to the frozen silence of its death, there's only one narrow window of time when stars burn and worlds form and minds can wake up to look at them. It is a vanishingly thin sliver in an ocean of hostile eternity, and you're living inside it right now at this very moment. Think about the two great darknesses this window sits between. Before it, there was the early universe, unimaginably hot and dense and violent. No atoms, no stars, no chance for anything like life. Just raw fire, slowly cooling. And after it comes everything we have just spent chapters exploring: the dead stars, the black holes, the endless cold. Two eternities of the impossible, with one brief, improbable stretch of warmth wedged in between. And life fits into an even smaller part of that already tiny window. The stars have been shining for over 13 billion years and will linger dimly for trillions more. But the era when the universe is truly hospitable, warm enough and calm enough and rich enough in the right ingredients for complexity to arise is thinner still. We are early in the age of stars, yes, and more than that, we are alive in the brief golden hour of the entire cosmos. We tend to marvel, rightly, at how lucky we are in place. That the Earth sits at just the right distance from the Sun, with water and air and a sheltering magnetic field, a rare oasis in a lethal cosmos. but we almost never stop to feel how lucky we are in time. We could have been nothing and nowhere at any point across an almost infinite span of dead eternity. Instead, we are here now while the lights are still on. And remember how we got here, because it ties the whole story together. The atoms you are made of were not there at the beginning. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was forged inside stars and scattered across space by the violent deaths we spent so long fearing. Supernovae built you. You are quite literally the debris of the cosmos, gathered up and briefly brought to life. So generations of stars had to live and die first, seeding space with the raw materials of worlds and bodies. That takes billions of years. And yet we also had to arrive before the cold set in, before the gas ran out and the stars stopped forming and the great dark began. We slipped into existence in the one span when the ingredients were finally ready and the fire had not yet gone out. A little too early, and there's nothing to build us. A little too late, and there is nothing left to build with. It puts every threat in this film in a different light. The asteroids are still out there. The sun will still swell and die. The stars will still go out. The black holes will still evaporate. The long dark is still coming, and nothing we have said changes a word of that. It is all real, and it is all on its way. But not one bit of it is here yet. The catastrophe is coming. The warmth is now. And into that warmth, something extraordinary happened. Something that, as far as we know, may be rarer than any of the disasters we have discussed. Matter woke up. Atoms, the very same atoms that make up dead rock and cold gas, arranged themselves here on this one small world into patterns complex enough to be aware, to feel, to wonder, to look up at the sky and ask what it all is and where it came from and how it ends. That is what we are. We're the cosmos grown, able to look at itself. Through our eyes, through our instruments, through every question ever asked, the universe became, for a brief moment in its long life, aware of its own existence. The stars have no idea they are shining. The black holes do not know they are there. But we know. We're the small, warm place where the universe finally worked out that it is here. And this is the part that moves me most and unsettles me most at the very same time. Because in learning to look, we also learn to see the ending. We are the one arrangement of matter that can understand the heat death, that can trace the death of the sun, that can stand under the stars and grasp that they are dying. We are the part of the universe that knows it is temporary. That is a burden nothing else in all of creation has to carry. For most of making this, I found that thought unbearably bleak. To be the only thing that can comprehend the dark, and to comprehend that the dark always wins in the end. What a cruel gift to hand awareness to a creature and then show at the expiration date on everything, including itself. I sat with that for a long time, and slowly, it turned into something else entirely. Because yes, everything ends. The earth ends, the sun ends, the stars end. The universe itself winds down into cold and silence. That is true, and there is no arguing it away. But here is the other half of it, the half that is just as true and far too easily forgotten. Everything first got to be. The stars got to burn. The world's got to form. And on at least one of them, life got to open its eyes and look around. The fact that it is all temporary is not a reason it does not matter. It may be the very reason it matters at all. A sunrise means something precisely because it does not last. This brief, warm, improbable window is not cheapened by the darkness on either side of it. It is made precious by it. The light is worth more, not less, for being surrounded by so very much dark. So the question that is left is not really about the ending, because the ending is not in doubt. The question is what we do with the window while we are inside it. And the answer this whole strange, frightening story keeps pointing me toward is almost embarrassingly simple. We look, we wonder, we try to understand, we hold on to one another. We keep asking what the universe is, knowing full well we will never see how the story truly finishes. There's a quiet defiance in that. and I have come to love it. Knowing everything we now know, knowing about the asteroids and the flares and the wandering black holes, knowing the sun will die and the stars will fail and the cold will win, we still get up in the morning. We still build things. We still fall in love and raise children and point telescopes at the dark and care desperately about the outcome of a story we already know ends in silence. I do not think that is foolish. I think it might be the bravest thing there is, to be small and temporary and fully aware of it, and to choose meaning anyway. To light a fire precisely because the night is coming. The universe spent billions of years and the deaths of countless stars to produce something that could stand in the dark and refuse to look away. That something is us. That is not nothing. That is very close to everything. I want to be honest with you, though, and not dress this up as a rescue. Nothing here saves us. The dark is still real. The endings in this film are still coming, every one of them, on their own vast and patient schedules. This is not a story where the danger turns out to be imaginary and everyone walks away safe. The lights really do go out in the end for good. But the wonder is exactly as real as the fear. Both are true at once, and I no longer think you have to choose between them. The grief that it all ends and the gratitude that it ever began are not opposites. They're the same feeling seen from two sides. To love something temporary is always to carry both, the joy of it and the loss of it, wound together and impossible to pull apart. And there has never been anything more temporary or more worth loving than this. So here's where I will leave you. Not with an asteroid or a dying star or the cold silence at the end of time. Instead, with something much closer and much smaller and far more astonishing than any of them. A single, thinking creature on a warm blue world, on an ordinary evening, standing outside and looking up at a sky full of stars that are already, every single one of them, slowly dying. That creature knows the stars are dying. It knows its world will burn and its sun will fail and the long dark is coming for everything, itself included. And it looks up anyway, because for this one impossible moment, against the whole crushing weight of eternity, the universe is warm, and it is awake, and it is aware, and it is us. That will not last. It was never going to last, but is happening now, and we were here to see it.